So, so good morning, everyone. Welcome to the second day, or the third, depends on how you count, for UCNC and the 6G Summit. This morning we have three excellent keynotes that will for sure give us a perspective on a lot of stuff, let's put it this way. We have one keynote coming from academia and two keynotes coming from industry. So from this viewpoint, I'm sure we'll get different perspectives on all the topics, all the areas that everyone is working here. So I would like to say also good morning to those that are seeing us via the web. This session is also being webcasted. So good morning, everyone, wherever you are. And I think people are still entering the room, so let's wait a couple of minutes and then I will introduce the first keynote and then we start. Okay, so again, good morning. So I forgot to introduce myself. So I'm Luís Correia. I am with the IST, the University of Lisbon. So let me introduce the first keynote speaker. It's Ted Rapoport. I dare to say that almost he does not need to be introduced, meaning he's a well-known professor in our area with an extensive, very extensive list of publications and work, well known for his work on propagation and other areas. It's really a pleasure for us to have him with us today and listen to his views and his thoughts on 6G and all the stuff that has to do with this conference. So he's the David Lee Ernst Weber Professor at the New York University. And I agreed with him that I would not reading his CV because then I would spend the 45 minutes of the talk reading his CV. So I'll give the floor to Ted. Ted, the floor is yours. Thank you.
Thank you. Thank you very much. Good morning. Thank you, Luis, and thank you all for being here. I want to say a special thanks to Tommy and to Eric and for the team here at Chalmers and to Luis for the invitation to this, my first EUCNC. And I've known Matti for years and have wanted to go to the 6G summit that he has and never could make it. So here I get both in one shot. So I'm really grateful to the organizers and to you, Matti. Excited to talk with you today about what I see that's likely to happen in 6G. And so I've got a lot of material, but there's really just two main themes. One is, what can we expect? And perhaps not surprising, I think we're going to go higher in frequency above the FR2 and 3GPP up to sub-terahertz. Also, I'll talk a little bit about upper midband, which is gaining a lot of traction. And then how do we make sure we make wireless sustainable? In fact, we're going to have a sustainable lunch today, I'm told, where we do smart reuse of fresh fruit in a special cake. So I think Europe's ahead of the US in terms of sustainability. So when you see some of the math on some of the new ideas I have in how to make sure we design wireless with proper and efficient energy consumption and less wasted power, think of our lunch today. And then I'll conclude. But first, I want to talk about this idea of moving to greater bandwidth. If you look at every generation of cellular from the first to today's fifth generation cellular, you see a huge step up in channel bandwidth each time. But safety and sustainability are really going to become so important to our industry, the way it is in the auto industry and the way it is in so many other parts of society. I think the wireless industry, our field, the ICT field, is going to face much more scrutiny than we ever had. And we started to see a hint of that in the rollout of 5G, and I'll talk about that a little more in my talk. If you look at the history of wireless, all of you know the first 4 generations were below 3 or 4 gigahertz. We call it sub-6 gigahertz in the 3GPP parlance, where in the radio spectrum, we understood the radio and microwave regions for decades. And then when cellular came out in the 1970s and 1980s, we started to move up to about 1 gigahertz, 900 megahertz, 1.8 gigahertz for PCS back in the early 1990s. And everything for the first 4 generations of cellular were sub-6 gigahertz. And then, kind of like oil fracking, released new sources of energy, or Moore's Law's increase in transistor capability, we suddenly found this great spectrum by moving above 6 gigahertz. And the reason for that is simple. Getting up to higher carrier frequency provides greater channel bandwidths for a particular fixed percentage around the carrier. So going up higher in frequency gives you for free much wider bandwidths for information transfer. Now, before we went full speed on showing the world that millimeter wave worked, I wanted to make sure it was safe. So I have an appointment in the med school, and with my colleague Chris Collins and graduate student Ting Wu, we studied the entire literature of millimeter wave research. Luckily, there was a lot known about millimeter wave. For decades, people around the world had been using it for diagnostic, surgery, skincare, beauty products. I mean, millimeter wave was well known for weapons in military. So there was a lot of literature and a lot of safety literature and a lot of studies. And so we wanted to make sure before reaching out to the world and showing that millimeter wave could be viable, quite viable for 5G, we wanted to study the world's known literature, and there was a lot out there. And the good news was it was only due to thermal damage of cells or thermal damage of tissue that you could see mutations of atoms and see rogue growth of cells. It was due to heating. There was no evidence, you could find no evidence of non-thermal breakdown of human tissue. Now, the irony of this paper, which came out and was since published in the National Institutes of Health, is that I was diagnosed with acute myeloid leukemia. And by the grace of God, I'm here with you. I have my little brother's DNA. I'm actually 8 years old. I have an 8-year-old immune system. And so a lot of the work I did on 5G and propagation modeling was actually from a hospital bed and chemo brain, and just, I thank God I'm alive. But this has become such an important issue for me, safety, because I believe, I can't prove it, that it was the ionizing radiation that I was exposed to during 1 week in the hospital in October of 2014 due to a heart problem, that all that ionizing radiation created the leukemia. I have no proof, but I went back and got all the medical records. I know I took over 35 millisieverts of radiation in a 1 week period of time, and it's well known that ionizing radiation can create abnormal cell growth and lead to cancer. In fact, if you look at NASA's 5 biggest risks for sending a human to Mars, one of them is galactic radiation that you're exposed to in space. So it's a real worry for me, and I think responsibility for our industry to start looking when we go up to sub-terahertz to just make sure that we go above 100 gigahertz. Let's make sure that there are no biological effects that could be harmful, because I think our industry is going to face a lot of scrutiny. And there's not a lot of research out there about the effects of terahertz. Terahertz is this unknown region. We know a lot about infrared and optical. We know that ultraviolet X-ray and gamma ray, which we're exposed to when we get above the troposphere and we go out into space, all of the radiation from space is ionizing, wavelengths up above visible light, but we know very little about terahertz. Yet, this is where the big bandwidth is, and I'll show in this talk huge opportunities for massive bandwidth. I just want to make sure we know it's safe, so I encourage the research community and government agencies to start looking at studies, animal studies, tissue studies, to make sure as we go higher in frequency there are any aren't any Heisenberg uncertainty principle problems or anything. We're still 4 orders of magnitude below the frequency of ionizing radiation. That's good news. Millimeter wave was 5 orders of magnitude below. And everything we could find and study said it was very, very safe. I firmly believe that. But as we get closer and closer to optical and ultraviolet, I think it's important we look at that. Now, here's why terahertz will happen and why I think it will be one of the moves to 6G. If you look at 2G, 3G, and 4G, look at the channel bandwidths. We had it 2 gigahertz back in 4G, 20 megahertz channel bandwidths. That's about 1% of a 2 gigahertz carrier frequency. If you look at 5G, say, take a 28 gigahertz carrier frequency, a 1% bandwidth is 280 megahertz, about a 200 megahertz bandwidth, which is what's allocated in a lot of the 5G allocations around the world for FR2 millimeter wave. So if you look at getting up to 1 terahertz carrier frequency, a 1% bandwidth is a 10 gigahertz channel. A 10 gigahertz channel bandwidth, which I'll show is very viable. And you think about a 10 gigahertz channel, you can get a lot of information through that. I'll put that in context in a minute. But the amazing thing is this is very narrow band. And when you're at very narrow band allocations, channel allocations, it's very easy to make antennas do what you want, filters do what you want, keep the phase noise down, build circuits, build radios that perform incredibly well so that this leap in carrier frequency doesn't degrade in other ways. Now, think about that 10 gigahertz bandwidth. What can we do and where will 6G take us? I want us to look at the human brain for a minute and think about how our brain processes. How do we think? How does our brain work? We have about 100 billion neurons, and each of these neurons are firing asynchronously 200 times per second, and each neuron's connected to about 1,000 others, which means we're processing at a speed of 1,000,000 billion operations per second. In other words, our brain is computing at 20 petaflops per second, 20,000 terabits per second, if you will. That's each one of us are doing this with our 30-watt brain. And when you think about our storage capability, our neurons are especially storage, so each of the neurons talking to 1,000 others. And so if you assume each neuron's 2 bits, we actually think it's 3 or 4 bits, we have about 100 million megabytes or 100 terabyte very rapid hard drive with 5 millisecond asynchronous access. All of us have that. So 100 terabyte hard drive, we could already buy terabyte hard drives today, and 20,000 terabits per second, that's a fast speed. But look at what $1,000 buys us. If you think about our smartphone today, $1,000 buys a smartphone roughly. And if you look at where we are today, today's technology, we're computing about 1 trillion operations per second in our smartphone with a lot of parallel threads. And if you project out to 2036, we will be in about 14, 15 years able to buy at commodity pricing computation comparable to the human brain. That's why you see all this interest in AI and ML today. It's actually predicting and moving towards this fact that we will be, in 15 years, able to buy commodity pricing with computational speeds comparable to a human being. Now, can we remote the human brain? And this is where I think one of the applications of wireless is going, whether we know it or not. The fact is, will this be 6G or 7G? I don't know. But let's go back to that 10 gigahertz RF channel and consider 1024 QAM, which we know is very doable. In fact, we could do 4 times better than that now in the 3GPP standard at 4096. Figure we get some kind of 1,000-time increase somewhere beyond MIMO, beyond massive MIMO. And actually, I don't need times 1,000. I just need times 250 because I already got 4 for free in the QAM. So some new modulation. And if we do that with a 10 gigahertz channel, we can get close to the actual real-time speed of communicating at the rate our brains process, 100 terabytes per second, 1/200th of the human brain. And if we had a 100 gigahertz channel bandwidth, we're at 5% of the human computational speed. Now, I want to make clear that computational speed is not intelligence. I call this wireless cognition, this idea. We developed in 2019, but wireless cognition with raw channel rate is not thinking, but it provides the ability to have computational processing transmitted from remote to the edge to a robotic device to actually be computing at the same speed of what we do today. So what's fascinating is the FCC in 2019, for the first time, opened up channel bandwidths that start to approach this 10 gigahertz bandwidth. In the Spectrum Horizons Act in 2019, FCC Chairman Ajit Pai and the commissioners voted into these 4 new unlicensed bands. They exist today. There are companies making products for these new bands above 100 gigahertz. They have EIRP limits. It's a 10-year license. But what's fascinating, if you look on the bottom left of this slide, is the FCC is using this to seed investment and to see if we can license this for mobile, if we can license this for fixed. So this is actually a playground of sorts to see if we can make this an actual spectrum allocation. And other countries around the world are harmonizing on this. Now, what applications can we do when we start to get up to the terabits or tens of terabits or 100 terabits per second? And if we could actually remote the computational speed of humans. You can think of drones, autonomous cars, robotics, of course. This whole idea of wireless cognition, having surrogates actually thinking or implementing in a robotic fashion in remote areas, exploring, so on. So it's an exciting future. There are a lot of applications. Our smartphone with this wide bandwidth, 5G is the first cellular standard that brings 2 new dimensions we never had in wireless. You think about it, it's really amazing. 2 brand new dimensions. The first dimension is very, very narrow band, narrow time-sliced symbols, very narrow symbols. We have much wider bandwidth, so we get much smaller symbol duration. So we have great time resolution down to the order of nanoseconds. And then the second thing you get is you start to get higher in frequency, the wavelengths become small, so you now get very small beam widths. You get much better spatial resolution. So we're getting temporal resolution and spatial resolution for free in 5G, and this is the tip of the iceberg for what's going to come in 6G. Now, there's a myth that millimeter wave and frequencies above 6 gigahertz are somehow lossy. And I want to get the facts straight on this. This shows you that the atmospheric absorption, this amazing protection that we have, the great creator gave us this protection of the troposphere, 10 kilometers on down, blocks us from harmful ultraviolet rays and galactic radiation. And that's where people focus on the attenuation and the loss. But if you look at this curve, you study it carefully, that when you're on ground level in typical atmosphere at ground level, look at the curve out to 400 gigahertz. We're only losing 10 dB per kilometer in up to 400 gigahertz. And that's only 1 dB per 100 meter small cell. And all the way out to 900 gigahertz, you can see at 900 gigahertz, down at the troughs, at ground level, we're 100 dB per kilometer lost due to the channel, due to the atmosphere, oxygen absorption, and so on. But 100 dB per kilometer is only 10 dB per 100 meter small cell. And 10 dB is only a factor of 10, which can be made up with more antenna gain when the wavelength starts becoming smaller than a human freckle. So there's really not that much propagation loss. And in fact, rain, once you get above 70 gigahertz or so, rain is no additional loss factor because the raindrop becomes much larger than the wavelength. So going out to beyond 70, 80, 90 gigahertz, you have flat all the way to 1,000 gigahertz or a terahertz carrier frequency. And what it shows is you could have several kilometers of wireless coverage all the way up to 400, and I claim 900 gigahertz. So 6G will move us towards this new regime where we start to see Moore's law coming to capacity with this new increase in spectrum. So I think 5G's killer app will be kind of the playground and learning about what's going to happen and bringing the technologies for 6G. And one of the big technologies that's happening is millimeter waves and developing the semiconductors and the knowledge and the antennas and the design tools, but also small cells. countries around the world are deploying smaller and smaller cells, or are enacting legislation to allow smaller base stations, smaller size cells to be deployed. And that's independent of frequency. Small cells are needed whenever you make the channel bandwidth wider, no matter whether you're at 1 gigahertz or 10 gigahertz or 100 gigahertz. So the Small Cell Act and the movement to small cells and the use of multiple antennas, MIMO, massive MIMO, will allow us to be able to support and engineer these move to higher frequencies and higher bandwidths. Now, one of the things that's caught a lot of traction lately, and I saw it at ICC in Rome last week, is this move to midband. And 5G Americas did a study on the midband spectrum in the US, and the FCC chairwoman, Jessica Rosenworcel, actually last year at the Mobile World Congress kind of started this move towards opening up the 7 to 15 gigahertz range. There's a lot of hope that we can get that spectrum at the World Radio Conference in UAE at the end of this year. It's going to be mainly satellite focused, but there's an opportunity for the wireless industry to get upper midband spectrum. And you can see other FCC commissioners also are focusing on this move above 95 gigahertz, including terahertz. So you see governments kind of aligning to this move to wider and wider bandwidth. It's just a natural evolution of every generation of cellular. So I think we'll expect that for 6G. One of the interesting things, though, is when you start to worry about how will midband, upper midband work, because there's not a lot known about the spectrum at, say, 16 gigahertz. I say that's an easy problem, nothing to worry about. If you look at the knowledge at 28, 73, and 140 gigahertz and go backwards to 15 or 16 gigahertz, you can really extrapolate. And what you see on this graph on the right is that as you go higher in frequency, the partitions, the walls, the obstructions, they become more lossy. So if you go lower in frequency, they become less lossy. You'll see this theme again and again. But the beauty of millimeter wave and terahertz and why it will work, and there are a lot of good talks at this conference I've seen, is that the mathematics show, I've already hopefully proven to you that the channel itself, the atmosphere, is not going to be a big factor up to 400 gigahertz. So once you remove the atmosphere and you start looking at the transmitter to receiver, what you see is that double directional channels using a directional transmitter and receiver antenna, the math shows you overcome free space loss and you way overcome any atmospheric loss. You totally overcome it. Look at equation 3. The received power for a given distance, for a given fixed physical area of antenna at transmitter and antenna at receiver, that is, keep the area fixed, go up in frequency, that means you give each antenna more gain, but keep the physical area fixed in your handset. Equation 3 shows that you get more power received at the receiver, not less. It's actually more power efficient to operate at higher frequencies. You get less consumption of energy per bit by moving higher in carrier frequency. Now, we've done a tremendous amount of work over the last 10 years plus at NYU, measuring indoor, outdoor. We have rotatable gimbals. We've published a lot. Some of you have probably seen the work. But I really admire the students. They really are like explorers going out into these environments and measuring these new frequencies. And what we found over the last 12, 13 years is really remarkable. I just want to give some highlights, which helps give us an answer about upper midband and going up to 400 gigahertz. And this is the real surprise. It turns out that if you use a simple physics-based reference of 1 meter, free space reference, for the calibrated received power from any transmitter and go into any of these environments, the path loss exponent, or the slope of received power or received power loss versus distance, is virtually identical over every frequency, 28, 73, 140. Here you can see that an omnidirectional path loss model in an indoor hotspot, NYU Wireless Lab Space and Offices, has a path loss exponent of 1.42. That is 14.2 dB per decade. That's better than the 2.0 or 20 dB per decade free space because of the waveguiding effect bouncing off the walls, off the floors, and so on. It doesn't matter what frequency band you're in. It's virtually the same model. And even in non-line of sight. In non-line of sight, it's 2.66, 26.6 dB per decade. At any of these bands, 28, 73, 142. The big difference in all these frequencies is simply what happens in that first meter, the dispersion of the radiated power out to 1 meter. This is really good news for wireless engineering. It means that things look to be pretty frequency indifferent. And that means the cellular system designs that are built for 5G, the small cells that are built for 5G, will inherently be the infrastructure which allows us to use the higher frequencies at 6G and 7G. The one difference, though, that you would expect is that as you go higher in frequency, higher in carrier frequency, from millimeter wave to sub-terahertz, you start to lose the diversity, you lose some multipath, you lose some of the weaker energy, and you are getting only more of the highlights of the strong signal components. You can see here for omnidirectional and omnidirectional non-line of sight, that as you move to the right, you start to have a smaller average number of spatial directions in which you receive energy. Similarly, you lose time delay spread. That is, you lose time dispersion as you go higher in frequency, simply because of the path loss and the less ability for energy to come back through multiple reflections and blockage and so on. The bottom line is there's still diversity even up to 140 gigahertz. And when you go outdoors, you find amazingly the same thing. We went outdoors over the last 12, 13 years, the streets of New York, Brooklyn, in many different environments, trying to emulate what small cells will look like in the future. And these are recent measurements at 140 gigahertz. And again, we find the same thing, going all over campus. And here's the beauty of working in a university environment that's not undergoing a lot of construction. We were able to, over a 10-year period, go to the same transmitter and receiver locations on the NYU Brooklyn campus over a 10-year period and recreate the exact same transmitter-receiver locations to get roughly the same measurement locations at different frequencies. And you are able to then understand how the physical environment impacts the propagation at different frequencies. And again, we found the same thing. And this is even adding some work we did in Texas. At 38 gigahertz, it turns out that the path loss exponent, or the power lost, the coverage, is really independent of frequency. If we reference to a physically based 1 meter free space model based on Harold Free's lambda squared over 4 pi d squared formula. So this is really good news. And this is what some of the actual measurements look like. We can get diversity, so we can use adaptive antennas to exploit the energy and create a link. And similarly, like we saw in indoor, as you go higher in frequency, you start to reduce the diversity. So you get down to about, you can see 1.9, so about 2 average angle of arrival clusters, directions, discrete directions where energy is coming from. The beauty of millimeter wave and sub-terahertz is that polarization works virtually flawlessly. And I'm going to show you, even in the factory environment, you get amazing cross-polarization discrimination. So even though there's only 2 angular arrival clusters, you use polarization diversity and you get 4 paths. So there's really, it's very nice. You actually have a rank of 4 if there's only 2 paths being made because of polarization diversity. And similarly, the time delay spreads decrease as you go higher in frequency, but there's still multipath. Now, we've done over 1 terabyte of measurements over the last decade, and we've made statistical channel models from all these measurements. We make it available for free. NYU Sim, it's open source. We're on our 4th release, version 4.0. We just put models in to 150 gigahertz from factories and urban microcell and indoor. So you now can use for free an NYU Sim MATLAB-based channel simulator, which will reproduce very realistically the statistics that we've measured over the last decade or so. And this is useful. A lot of our sponsors, a lot of the industry are using NYU Sim for their own modem design. It has different characteristics, different rank. It's more realistic because it's based on channel measurements. And so this is a very powerful simulator, so you don't have to do all the work, that hard work that all these students have done over the years. And what you see is you actually get better performance at millimeter wave and terahertz than what using the 3GPP channel model would give you in terms of bits per second per hertz in hybrid beamforming multi-user scenario. We published that stuff several years ago. But the important thing I want to mention is that if we're going to make sustainable wireless, and sustainability, I believe, really will become a focus for our industry. I think we're going to be in the crosshairs of the press and of society as our industry becomes a bigger consumer of power, is when we make design choices or when we do research, I think we really need to consider the power consumption. You know, digital beamforming is a great idea, it's a great research project, but we need a way to measure and parameterize and characterize the power we give up in providing all the DC power to all the components versus hybrid beamforming. There's a trade-off between energy consumption and performance on the link, and all that has to be integrated. I'm going to talk about that at the end. But this is a tool that you can use, and this is something also that the public's going to be increasingly looking at us for, this idea of safety, not just sustainability, but safety. I want to talk about a terahertz co-sharing spectrum project. But before I do this, I want to ask you, do you remember 5 years ago when the United States weather forecasters were saying that 5G was going to ruin the ability for people to predict the weather? Do any of you remember that? Okay, a few of you do. Let me ask you this. Do you remember about a year ago when the popular press in the U.S. started to report that 5G would cause airplanes to fall? Remember that? Yeah. Okay, they're the same problem. They're a spectrum co-sharing or an adjacent spectrum sharing problem. And the bottom line is interference. In terms of the weather thing, it was 24 gigahertz millimeter wave band starting to be rolled out, and there's 5 satellite channels, these very, very sensitive satellites that have virtually zero noise receivers up circling above space, measuring noise to see if there's water. That is, they're basically radiometers looking for noise. So any energy that gets up into the satellite can cause a false alarm. And so there was the 5G 24 gigahertz spectrum was a few hundred megahertz away, and they were afraid the spectral mask would leak in to one of the 5 bands. Now, I don't know about you, but the weather's half off without any 5G, so I didn't see it doing any big difference. But the issue about the airlines was the new 5G spectrum at 3.4 gigahertz was close to the altimeter frequencies of some plane radars. But this is a big issue because it's one of the big impediments to getting spectrum up at terahertz. I want to show you this. We put a satellite up on a roof of a building at NYU to be a surrogate satellite looking down on Earth. This would be replicating one of those super low noise radiometers that are simply detecting energy. And when you look at the problem of satellites, and satellites have to worry about any emission from Earth because it can look like an interference source. Now remember, we have this great troposphere that protects us. So if we're on a slant path looking on the horizon, that if mobile can keep its energy on the horizon, we're able to really have this great protection, virtually infinite path loss. That is, any energy on the horizon is not going to interfere with the satellite on the horizon. You can see this in the graph. We have thousands of dB of path loss due to the troposphere, due to a long slant path. But if you're going directly above, we only have about 10 kilometers of absorption loss. So looking right above to a satellite with a transmitter aiming at the satellite creates a huge interference problem for satellites. So right now in the US and ITU, and this will be an issue discussed at WRC, I believe, you have spectrum allocation right now out to 275 gigahertz. We're going to go higher. But there are these restricted bands where satellites are operating and protected, and you can see them in gray. And then we have the green Crow primary, which are spectrum availability bands for where 5G and 6G could go to terahertz, sub-terahertz. And one of the concerns is there's not a big contiguous spectrum allocation for mobile right now. I mean, it'd be nice if we go up to 200 or 300 gigahertz. If we go up to 300 gigahertz, it'd be nice to have a 25 or 30 gigahertz spectrum allocation to allow carriers to operate, have a couple carriers, three different wireless providers competing and offering service. Right now, that doesn't exist because of all these satellites that operate protected. So we went out and made satellite surrogate measurements. You can see on the right is the satellite receiver looking down. And this was during COVID, of course. And the students went out and they took a transmitter at the street level all around campus at different distances. And they moved the transmitter in every possible direction, every rotating angle. And we, at the receiver up on the roof, looked at every possible angle. And we went to many, many locations. And the only thing we could ever find was when we pointed the transmitter on the ground up and at 20 degrees, and it happened to bounce off a sign, and the receiver at the satellite was able to find it with one particular pointing direction. And this is what you found. We found the line of sight path, which you'd expect to have, because there's, because of the fall off on the beam. Remember, this is not a satellite hundreds of kilometers up. This is, up on a building 70 feet, 30 meters. But this was the only place we could find. And while this is a busy slide, it shows, look at the bottom curves at 0 degrees, 8 degrees, and even 16 degrees. If we can keep the energy below 15 degrees on Earth of every base station and mobile, we're able to ensure that we're way below what would even be the noise floor seen by a satellite way up in space. So this is good news. It means we could move to co-sharing if we design our antennas to always be on the ground and always on the horizon where the mobiles are, and to avoid going up in space. I think that'll become more and more of an issue as you see wireless go wider and wider bandwidth start to expand our elbows with other services. Now, our latest measurement campaign has been in factories. We've been in 4 factories in the last year studying 140 gigahertz. And it's really fascinating. I don't have time to talk about it. But what's really amazing is factory at millimeter wave started in Sweden, 2015. So, this is where you were you were one of the first to look at millimeter wave channels in factory buildings. And we've just done the first work at 142 gigahertz D-band. And what you find out in factories is, of course, there's a lot of reflection, so it's more time diverse than indoor hotspot. There's more time delay, there's more angles of arrival, and there's really a difference between a tall receiver and a small receiver. We studied both a human receiver height, 1.5 meters, and an AGV height at half meter above the floor. And there's a big difference. In fact, let me show you some of the locations. You can see on the far right, that's our low receiver height where it's rotating, looking for energy. And you can see we went into a bunch of different kinds of environments. We just presented this at ICC, so I won't talk about it here, but I will give one result of the many results that we found. And what's really cool is even in the very cluttered environment of the factory, the cross-polarization discrimination is still almost as good as the antenna. That is, as you go higher in frequency, you really preserve the cross-polarization discrimination. And I started my PhD work in factories, and that wasn't the case down at 1.3 gigahertz. You had less cross-polar discrimination. You go higher in frequency, you get much more discrimination, which means you get much more polarization diversity, and you get free rank. Okay. So let me conclude with this part of the talk, and I'm going to end with one other idea. There's a lot of great work that's been done around the world, and all of it seems to be corroborating the idea that millimeter wave and terahertz works. It physically is possible. This satellite terrestrial interference issue, I think, is going to become more and more of an issue in our field. I think it's really a wonderful opportunity, especially when I see here in Europe that there's so much work in non-terrestrial networks. It's not like that in the U.S. So this conference has been really good for me in opening up my eyes to see that maybe satellites and 5G, 3GPP, maybe that will someday integrate. But right now, you know, they seem to be working at different odds, and certainly for the passive satellites, wireless is very scary. Now, Luis, I want to just take a couple more minutes, and I have a bunch more slides. I'm not going to go over them, but since sustainability is so important, I'd be remiss if I didn't talk about this challenge for all of us, and that is, how are we going to conserve energy, and what are the key performance indicators that we can develop for cellular, for Wi-Fi, for computing? I mean, we can do all this great work with AI and ML, but if the cost to do that computing gives us very little incremental gain, we've cost the planet a lot of energy for a gain in one area that's hurt us in another area. And we don't really have KPIs to understand that. And it's going to be a big deal as we go to 20 to 30% of the global power consumption in our industry. And so I want to set this up. I've been thinking about this for a decade, and we developed something I called the consumption factor and power efficiency factor with a brilliant student, James Murdoch. And what James did is he thought about an IoT device of the future, this simple homodyne transmitter, and he thought, how can I figure out how to build the most power efficient homodyne transmitter, a tiny little IoT speck of dust? How can I design that most efficiently to use the less power? And it's really a fascinating problem because there's no display, there's no ancillary components, there's no other big power consumption other than getting the signal from the sink to the source or the sink to the radio channel. And what he realized, and I give him a lot of credit, is equation 21, is he figured out that the power consumed of any device, whether it's your laptop or your TV or your cell phone or a mixer or an amplifier, is the power consumed in a communication device is simply the power that's transferred in the signal plus the power that's transferred in the non-signal part that enables that signal being carried, and then it's all other stuff. That is, if you look at figure 4, any communication system, any network, any device, any circuit, any end-to-end system has a source and a sink and components on it that either carry the signal or don't carry the signal. And the total power consumed is simply the superposition of the power of all the non-signal stuff and the power of the signal stuff. And what you find out is this is exactly what Harold Freese did at Bell Labs in 1941 to develop noise figure. Noise figure was developed to figure out how much additive noise is created by devices on a cascade. Our problem as an industry is to figure out how much additive waste is created on components in a cascade. That is, 80 years ago, the enemy of planet Earth was signal-to-noise ratio and trying to build radios. We had vacuum tubes. We didn't have broadband. We didn't have cellular infrastructure. We were trying to listen to them, you know, deep space and short wave. And now we have all this great capability and transistors and semiconductors and base stations. And so now we have to worry about what's the new enemy. The new enemy is, you know, how to make a sustainable future. If you go back and do the exact same math that Harold Freese did for noise figure and noise factor, we did this and we came up with waste factor and waste figure. It's a virtually identical approach, except of instead of looking at the, and by the way, Nokia has used this to study their high-altitude platforms to figure out that it was less power costly and more earth-friendly to actually use a repeater than an actual base station in the aerial platform. But we published this just a few months ago. But the bottom line is, if you look at noise factor, we're trying to figure out the things referenced to the input. Because in Harold Freese days, it was energy coming into the antenna being transferred to our detector. So we were interested in what's coming at the input. and figuring out what's at the output. Harold Freese could have looked at the output at the detector, but he wanted to look at the antenna because you don't know what's out there. It's just coming into the antenna. Instead, we look at the output power. We refer it to the output. And from this, you can then develop a waste factor, W, which tells you if you know the output power, you multiply it by W, that's the total power consumed. So we have really, I think, the beginning of the first KPI to start looking at how much power is wasted. And I just want to show you, this is noise figure. The same idea can be applied to this idea of waste factor, where the power of the waste factor is a cascade, just like noise figure. You get a waste factor, which is a cascade. So we could start quantifying transmitters or hybrid antennas or mixers with a W, just like we have a noise figure on a spec sheet. You know, every amplifier or transceiver has a noise figure in its spec sheet. Any receiver you buy has a noise figure. We should start doing that for waste figure because it's very easy to quantify. So 80 years later, we have W, which is waste factor. And all waste factor is all you need to know is the gain and the efficiency of each device. The gain and the efficiency leads to waste factor. So I'll leave it at that. I'll show you. So I'll just ask you one final question, and I'll end the keynote. So if you have three components, an RF amplifier and a mixer and a baseband amplifier, they have a gain and an efficiency. And with that, you're able to figure out the waste factor for each of those components. So for case 1, choosing these 3 components, you get a waste factor of 4.85 dB. And case 2, you have an amplifier which has a little less efficiency, baseband amplifier with a little more efficiency. You get a waste factor of 5.41 dB. So which design do we want to save the planet? Do you want case 1 or case 2? The answer is case 1. You want the lowest waste factor. Just like noise factor or noise figure, where F equals 0 dB means no additive noise, a waste factor of 0 dB means no wasted power along the signal. So a W of 0 dB is no power is wasted and everything from the source gets delivered to the sink with no waste. So you want the lowest waste factor in order to have the best power efficiency and least waste. I'll leave it at that, and thank you very much. Appreciate it.
Thank you, Ted. Thank you very much. Excellent talk. Thank you. So we have time for a couple of questions. Can you please put up the lights? And so there are microphones around the room. So anyone? Yes, please. Please identify yourself.
Hello, I'm Jean-Laurent Plateau from Tara. Great presentation showing us the future with wider bandwidth and meaning going higher in carrier frequency. So if we jump and go even more in the future, higher in frequency, you end up in the optical domain in the hundreds of terahertz. And there are technology already out there in free space optics. So what's missing in free space optics to be also the future? What should people working on free space optics?
It's a great question. And free space optics works great when there's not the sun. I mean, the bottom line is the biggest noise source is the sun. I mean, it is such an intense noise source, and it can reflect off so many things. That's the big limit to free space optics. It will work great in dark data centers, phenomenal. And I think it's already working there. Tunnels, terrific. But whenever there's any source of light from the sun, which is such a potent radiator, it just can't compete with signal-to-noise ratio.
One more? Yes, please.
I think also inside boxes, we'll see that. I mean, we'll see more of that. Optical interconnect works great as long as you can keep the light out.
Yeah, hello, thank you for the talk. So it's also my first time attending you live as it's your first time in a USNC. So my name is Ahmad Nimr from TU Dresden. My work is more in the signal processing part. So now when I look at this enormous amount of data rate you're talking about, 100 gigabit per second and more, then it is scary for me for the signal processing.
Yeah.
So this is the first issue. So when always talking about sub-terahertz, we just talk about the data rate. But what about the energy consumption? So this is also related to your previous or the last slide. And then the other question is, we have also you mentioned the power efficiency for sub-terahertz. So how you can see that using this sub-terahertz even for the IoT devices?
Yeah, no, that's a great question. And you probably work with a great colleague of mine, Gerhard Fettweiss, if you're at TU Dresden. Look at how the microprocessor world has scaled computing speeds. You know, our clock speeds haven't gone up as much, but the parallel threads have increased orders of magnitudes. We now have dozens or even 100 or so parallel threads computing. So I think the key is parallelizing. That's how our brain works. We parallelize. So that's where I think KPIs like waste factor really come into play. You know, what works best? What's the best way? You can't build ADCs. They're so power hungry if you keep getting them faster and faster. So will 10 in parallel at 1/10 the speed with time slicing work just as well or close to just as well with much less power? I think that's a way we address it. I think we have to parallelize the problem and somehow deal with time slicing and time overlapping in smart ways. And then we have to look at the physics, the actual physics of building the devices. What's the most efficient way? I mean, we think in wireless coherent versus non-coherent. You know, there's 3 dB power penalty to go coherent. What's the cost? What are we spending in energy to get that extra 3 dB in the link? So I think it's an open question, but I think going parallel is going to be the key to that.
Okay, thank you, Ted, once more.
Yeah.
Just a small token of our appreciation. You can keep warm coffee in there. Thank you again. Thank you for coming.
Thanks, Luis. Thanks for the invitation.
Thank you.
Take care.
So Ted will be around at the coffee break. I'm sure he'll be available to answer your questions and to talk to you. So we need to move now to the second keynote of this morning. So it's Peter Vetter from Nokia. He's the president of Bell Labs Core Research in the US. And Peter is bringing a guest. And the guest is Takahiro Nakamura. So Nakamura-san is the Senior Vice President for NTT DOCOMO. So I thank Peter for being here and for inviting Takahiro, and Takahiro for accepting to be here as well. Guys, the floor is yours. Thank you very much.
Thanks, Luis, for this kind introduction. And yes, we are going to innovate a bit in terms of giving a keynote because we wanted to give a bit of a dual perspective on the future of 6G. From a service provider perspective, what are the use cases, what is the deployment, and from a system vendor perspective, what are the new technologies that we see happen for the 6G era. So I'm also very pleased to be in the same keynote session as Ted Rappaport. I can say that NYU and NTT DOCOMO outside of Europe are our most important 6G research partners. So we titled our talk 6G Getting into the Next Gear. The main point will be that we're getting out of that exploration phase of research, and we are seeing tangible first proof points of things that can be done for 6G, and we need to start thinking of the systematization and getting ready also for the pre-standardization efforts. It's already the 5th 6G summit. I still remember the very first 6G summit when Professor Matti Latva-Aho has put this giant 6G sculpture on stage. And that was really the first time that we at an event started talking about the 6G vision, and both Nakamura-san and myself, we were speakers at that event. Since then, 4 years later, a lot of things have happened. We had a first round of research projects, European-funded research projects, including the flagship project HEXA-X. In the European context, more than 20 initiatives were taken by over 150 organizations. In the meantime, the SNS, the Smart Network Services Joint Undertaking, has been created, and there is a commitment for 1.8 billion private and public funding for the next 5 years in 6G research. 35 projects already accepted in that, and including there also the second phase of HEXA-X, the flagship project. And then also if you look in the media, more than 2,000 articles and other media, video blogs and such have been published. And then important for the research community, if you do the search on IEEE Explore, more than 6,000 research papers on 6G. So lots of things have happened already in 6G, and we're really getting into that next year. When preparing this talk, I said, let me look back to what I said in Levy. And one of the main points, I made a reflection of the generation every decade. And every generation is defined by three defining attributes. There must be a defining new application. There must be a defining new radio technology, aiming for higher and higher frequency bands with wider and wider bands, as Ted so eloquently explained. And then there must be a defining new platform technology that enables the new applications as well as the new networks. And the icons speak for themselves. I don't need to talk through all of them, but just to anchor a bit that thinking for 5G, that defining application has been industrial automation. The defining new radio technology has been 5G millimeter wave. In the meantime, we have seen that most of the deployment happens with massive MIMO technology in the midband. So there's a bit of a reflection and lesson learned that we need to take into account for going forward to 6G. And then the defining platform has been distributed compute in distributed cloud to enable low latency applications as well as enabling cloudified network functions. So in 2019, we already started defining what is the application then for 6G. And we recognize this importance of the fusion of digital and physical worlds already at that time. In terms of new radio technology, we started thinking of, hey, let's go to even higher frequency bands, sub-terahertz, where there's wider bands available. And then the defining platform for compute and also for new network designs, AI. So one more thing before I get there. Every generation in the European context is also defined by a defining flagship project. The European research programs have been very foundational in laying the groundwork for every generation. And you can point to a flagship project, say for instance for 4G, that was the Winner project, and there was an overarching umbrella organization, the World Wireless World Initiative. In 5G, we had METIS as the flagship project, and the overarching umbrella was the 5G private-public partnership. In 2019, we started defining and creating the consortium for the, you have the animation there? This is how it works, yes. In 2019, we started the creation of the HEXA-X consortium as the flagship project for 6G. Now, 4 years later, HEXA-X is coming to an end and starts its second phase. Let's have a fresh look at these. So the defining application, we see the confirmation of that digital physical fusion. Metaverse became a thing in the meantime. We become a bit more cautious on the excitement about sub-terahertz. All credit to academic research like Ted Rappaport, but lesson learned. Mid-band deployments is the dominant thing in 5G. There's another very important band that we need to look at, that is the 7 to 15 gigahertz, the upper mid-band. And then third, in terms of defining compute platform, yes, AI very much confirmed what it can do for the radio interface as well as what it can do for the way we network. And we're going to structure our keynote according to these three big aspects.
Okay, so from here, I'd like to explain the 60 applications, especially for the digital physical fusion. Next. Yeah, actually, digital physical fusion is very, very important, even for now, to create a new business for us, for operators. but that will be more essential in the future. And also, we believe that digital physical fusion can augment the human possibilities enabled by the metaverses. And we have 3 kinds of metaverse, we think, and industrial metaverse, enterprise metaverse, and the consumer metaverse. And the industrial metaverse is OT-centric, and maybe industrial automation focus, and also OT, or operation result driven. Enterprise metaverse, this is IT-centric, of course, and that can be enterprise business driven, and that will be boosted by the evolved XR devices and immersive virtual space application and so on. And the consumer metaverse, that is of course a consumer appeal driven. And also maybe excellent XR devices can boost this growth. Okay. And this slide shows growth of the metaverse segments, 3 metaverse segments. Clearly, we can see that significant revenue potentials in all of these 3 metaverses. But growth speed is different. It seems that the enterprise metaverse and the consumer metaverse, the growth speed is a little bit slow. We need to wait for the excellent XR devices and nice applications for several years to boost the growth of these metaverse. On the other hand, industrial metaverse, the growth speed is faster than the others, thanks to the early traction of the industrial automation solution applicability. And yeah, next please. And I think that for that, the 6G infrastructure taking a very important role. And in this case, for the digital physical fusion, the huge amount of data of the physical world and the human world need to be transferred to the digital world. And then that data will be processed, analyzed by AI in the digital world, and quickly actuated to the physical world. In order to do that, our 6G infrastructure has a very, very high performance, such as the extreme high data rate and the capacity, and the extreme low latency, and the extreme high reliability. These are the further improvement of the 5G capability. And also, we need to realize by the 6G infrastructure the extreme coverage to connect the unconnected. And also extreme low energy and the cost. This is, of course, very important for the sustainable society. And also extreme massive connectivity and the sensing. The accurate sensing capability is very, very essential for the digital physical fusion in the 6G era.
Yeah, I want to pick up on that sensing capability. So indeed, to enable the synchronous update of the digital twins in the digital world with the physical world, you need massive deployment of sensing. And 6G has an opportunity for an additional sensing modality that then can be fused with other sensing modalities, and that is radio. Because we will have radio all around us for the communication, but we can use these radio signals also as a radar. So joint communication and sensing. We're not inventing the radar itself, but the key point is that we do this jointly while maintaining the quality of service of the communication system. So, and what can you do? You can do localization of humans and objects with an accuracy of tens of centimeters. You can even detect shape. You can have Doppler effect and see motion. You can also see motion of chest, breathing, heart rate, so vital signs. And you can then, using AI, deduce higher order meaning. When I see chest movement or so, oh, this must be a mammal or a human. If I see the frequency component of a rotating fan, that must be a piece of equipment there. So there's higher order meaning that we can deduce applying AI to the sensed signals. So we've built the first proof of concept using an OFDM 28 gigahertz 3GPP millimeter wave system. We took great care that we can really do that joint communication, and we have algorithmic innovations that optimize the quality of service of the communication and optimize the beamforming for maximum resolution for the sensing application. And we then have the combined intelligence, so there is on one hand the enabled millimeter wave access point, but then also additional sniffers, as you can see in this picture, and then additional offline process. It's actually real-time processing to make sense of what we see. For those people that have been at Mobile World Congress, we actually demonstrated this live at Mobile World Congress, and to create a bit of an experience, we created this giant piano along the wall, and while you were walking along, the system behind that screen, that 28 millimeter wave access system, sensed the location, and so you could play the tune of that piano. And to show that it is real, we actually then also blocked the millimeter wave system, and then at that moment the piano stopped playing. So it was a real live system going on. But there's more that we can do. Joint communication and sensing is not only in the radio space. As you maybe have noticed, Nokia has a new brand, a new logo, and the A in the logo actually also looks like a lambda, and that stands for wavelength as in radio, but also optical wavelengths. And the future 6G network, it's not only about the radio, it's the end-to-end network, and the optical transport network will be an essential part of the future 6G network. And also in optical fiber networks, you can apply sensing. Actually, here in Göteborg, we have a trial going on with aerial installed fiber cables. And you can use coherent optical communication systems to see phase shifts. And when you apply mechanical strain, you can see subtle differences. Subtle differences that, for instance, help us to estimate wind speeds and predict possible, if there's very heavy winds, the breakage of cables. We can also detect temperature, and that can help us localize potential fires, God forbid that they happen. Also in transoceanic systems, much longer systems, at the bottom of the sea where it's a lot quieter, we can detect wave motions of tidal waves, of tsunami waves, and start predicting the tsunamis. We can see the passing of a ship or the dropping of an anchor. So very interesting use cases that you can use from that. Also DOCOMO, in the context of IOWN, is working and researching the capabilities of fiber in urban infrastructure to sense the traffic.
Okay, so use cases of the radio sensing. We have already discussed so much about the variety of the use cases for the radio sensing in the 3GPP. But I show that 4 typical use cases here. And what's one is the detection of the intruder to railway. This is very useful solution, use cases for the railway company for safe operation. And if we can detect the wild animals on the railway, maybe we can take a proper action for the emergency stop in advance. And congestion detection. This is very, very typical use cases for the radio sensing. And maybe we can use this kind of the use cases, solutions for the shop, theater, restaurant, and the event venue, and so on. And behavior health monitoring. This could be useful and essential to save human life. And local rainfall estimation. This is now very useful due to the global climate change. And in Japan, we have serious disasters due to the local rainfall, so-called guerrilla heavy rain in Japan. And yeah, if we can detect the local guerrilla heavy rain very quickly, maybe we can use that kind of information to mitigate the damage. Yeah, please. And also, we believe that we can monetize digital physical fusion by the sensing and AI. This is a high-level example of the architecture of the sensing and the AI. From the bottom, yes, maybe we can have several kinds of the sensing measures, including the joint communication and the sensing, and also sensors implemented to our network facilities. And also for the future, HAPS or NTN, maybe satellite HAPS can install the sensors or cameras. The data detected by those kind of the sensors should transfer to our operator's MEC and stored, analyzed by AI and controlled. And those kind of the data can be used for the many kind of the use cases for our business. Of course, the applications should be developed, installed to our operator's MEC, but together with the variety of the partners, so that we can develop the very excellent applications in agile manner. And of course, the applications in the internet, public cloud, should be used by cooperation with the other systems and stakeholders.
Okay, so we talked about the defining applications. Let's move to the next, the defining radio technologies. And as said, I want to talk about the 7 to 15 gigahertz as what we will call the golden band, the upper mid-band for 6G, and then also exploring what sub-terahertz can do for 6G. This is a well-known figure. You recognize the spectral bands for 4G and 5G that are currently used, and you see also their range. So you have the low band that really provides the wide coverage. Then you have the mid-band where we apply massive MIMO to achieve high capacity. And then you have the millimeter wave with limited coverage and small cell deployments in hotspots for extreme capacity support. And we can expect that in 6G we will repurpose these bands also for 6G applications and allow for flexible sharing of spectrum across generations. But there's two important new bands. So there is the 7 to 15 gigahertz. And our simulations show that you can have a nearly same coverage as with the current midband in that upper midband. And that provides an excellent opportunity to provide high capacity from existing cell sites. Because lesson learned from 5G, if you can provide the capacity from existing cell sites, then that's what will be done. And then for the extreme capacity, we see a future in repurposing the millimeter wave, and then the terahertz that has even smaller capacity, yes, in small cell deployments, and we see a future there if there is additional capabilities for value creation in terms of using it for sensing with higher accuracy. So let's first look at the upper midband. And I want to start by saying that with distributed massive MIMO, you have already a first opportunity to enhance capacity. We've demonstrated that and did a technical trial with AT&T in the current midband 3.5 gigahertz. And we see that really as a stepping stone and a technology that we can then also use in 6G. But to really get to that almost same coverage, you will need many more antenna elements in your array to have the finer beamforming. It will be digital beamforming because there's a lot of angular spread that we need to deal with. So there's some considerations on hybrid beamforming and digital beamforming to find that right optimum. Physics is on our side. Half the wavelength means that in the same form factor you can fit 4 times more antenna elements. It's mainly how do you do the processing in an energy efficient way that will be an important challenge. And a direction, and that's why I introduced the distributed massive MIMO, also a modular approach and a distributed processing within the panel is a more energy efficient direction and a lower complexity direction that we're looking for. Then in sub-terahertz, we do invest in sub-terahertz radio transmission and research. The earlier applications that we see, that we definitely see happen is 100 gigabit per second for wireless backhaul and front haul. An important challenge is not only low-cost RFICs at those high frequencies, but then also the packaging. The classical PCB technology with epoxy have too much of an attenuation at the frequencies that we're looking. We need new materials. We're researching radio and glass. And it's not glass as in transparent, it is really the material property that shows lower attenuation and permittivities that are more amenable for these high frequencies above 100 gigahertz. And you see here actually an antenna design, a large array antenna, and on the backside we flip chip bonded our RFICs. Also important is then research of new waveforms. We experimented over the air to really achieve a more energy efficient signal processing and taking into account also the phase noise, for instance, that happen at those frequencies. And then as Ted Rappaport has done already quite a lot of pioneering work in that space, we need lots of data samples in different environments, urban, suburban, tree-lined streets, and what have you, and indoor, to have accurate channel models at those high frequencies. And not only for the communication, but to what we said earlier, also how do these channels behave for sensing the reflectivity of surfaces and so on. And then there's a whole set of technologies that apply to any of these frequency ranges, really, the upper mid-band, the millimeter wave, and the sub-terahertz, to enhance the coverage at a low cost. And Docomo and partners and Nokia and partners are looking into these different technologies. And here, for instance, we do have antenna on glass, and here it is about making the antenna invisible. Also, low-cost pinchable antenna arrays, new and fresh looks at front haul, revisit the analog over fiber, orbital angular momentum over the air, and then also repeater systems, reflectors, in reconfigurable intelligence surfaces, or also passive lenses.
Okay, so I'd like to explain why we need a higher capacity in the 6G era. And this slide shows the forecast on the global mobile traffic per year, traffic increase, and also global radio capacity increase. And the left-hand side shows the increase in the traffic. As you may know, our traffic is increasing continuously by 1.2 to 1.5 times a year. And especially, we need to take care about the AR/VR traffic, as shown in the purple bar, and that will be increased drastically in the future. So for the non-AR/VR traffic, green part, maybe for the only that traffic, maybe we can cover the existing spectrum resources like sub-6 with the 5G technologies. That can be enough. But to cope with the AR/VR traffic that will be increased drastically in the future, we need additional frequency resources, spectrum resources around sub-7 gigahertz with the 5G advanced technologies by the 2030. But after the 2030, traffic will increase more and more, and we will need further additional spectrum resources at the 7 to 15, higher mid-band, with the 6G technologies to cover that. Next, please. And what kind of the use cases can be considered using the higher frequency band? Of course, higher capacity use cases which need a higher capacity, especially for downlink, peak data rate above 100 gigabps. Maybe we can consider the variety of the use cases for the future, but one of the examples should be as you can see, the left-hand side, realistic human-to-human and the machine interaction in the healthcare and the enterprise. And in the future, we can use the very excellent AR/VR devices and also excellent metaverse solutions and also photonics and everything. That can be used, and also we can provide a very excellent services like human-to-human, human-to-machine, and so on. And also the higher frequency band use can provide additional benefit. That is very accurate sensing with high resolution thanks to the very short wavelengths. And with that, technologies maybe realize that kind of gesture recognition use cases, and also autonomous driving. That autonomous automotive industry need a very, very high resolution, high accurate sensing, positioning accuracies. So this should be a good example of the use cases. Next, please. And also uplink. And even for now, our customers need a very high performance uplink, especially for the remote control and the remote surveillance use cases. But for the future, in addition to that, as I said, the digital physical fusion world will come. And a huge amount of data need to be transferred to the digital world. The state of the physical world, for example, the city data and the factory, farm, and also vital signs of the human body need to be transferred to the digital world so that we can support the development in the industry and the well-being society.
Okay, so we arrive now after the second pillar, the defining radio technology, now the defining platform technology, AI. And staying with the radio interface, we'll see what that can do for the physical layer connectivity, AI, but then we'll also look at the importance of AI for future network architectures. Let's start with the radio interface. So you see here the classical design of a transmitter and a receiver with its respective functional blocks. And there's already a large body of research on how you can optimize these individual functional blocks like synchronization, channel estimation, equalization with machine learning. Now, at the interfaces of each of these blocks, actually information gets lost. So we realized that if we start integrating some of these blocks and treat them as a whole, more information is maintained and you get to more accurate learning principles and better performance. So we devised this deep learning receiver that not only provides better performance, but actually there's also opportunity for simplification because you can then start thinking of reducing the total number of layers in your machine learning. Notice that you can do this already in 5G or 5G advanced. It is localized in the receiver. If you start defining a new interface, then there's lots more that you can do because then you have a feedback loop across the transmitter and the receiver. You can optimize at the transmit side, new waveforms, self-learned waveforms. You can optimize the beamforming, and that in conjunction with transmit and receive over a newly defined air interface. And we've built it this 6G end-to-end AI system for real with a deep transmitter and a deep receiver. Some of you may have seen it in our Nokia booth. And on the right-hand side, you see a self-learned waveform. And it's really amazing how AI comes up with an optimal constellation depending on the instantaneous channel condition. And compared to the quadrature amplitude modulation, this is much more intuitive to have these polar constellation in I and Q space, and there is an asymmetry, and if you think of it, that also makes sense because you have more phase information, so you can get better performance in that. On that GPU-based system, we implemented a classical radio as well as an AI air interface, a native AI air interface, and we see performance improvements of up to 30% using these systems in fast-changing channels. Pedestrians is up to 18%. So there's significant improvements that we get. But there's an important challenge here, that AI processing requires quite some energy. And so in conjunction with this research, we also need to look at new ASIC technologies that lower the total energy consumption, that allow for more operations per second per watt. And some of the directions are compute in memory and analog and mixed signal compute. In our research at Bell Labs, we also look at optical computing and how you can create optical neural networks. And this is promising for inference at very high line rates. So to achieve high speed applications going really to the hundreds of gigabit speeds per second. While we use AI and trying to approach Shannon limit, it's also a good moment to pause. And Shannon at Bell Labs, he wrote that famous paper, and in the introduction, it was actually his colleague Weaver that said there's actually 3 levels of communication. There is the communication of bits and symbols. There is the communication of the meaning, the semantic communication as a second level. And then as a third level, there is, do I really achieve my goal, the effective communication? And Shannon famously said, well, that the meaning and achieving the goal, that's a human problem. The real engineering problem, that's the transmission of bits and symbols with minimal error. And that's what we did for decades. But now that the endpoints become machines, and with AI and ML, the conveying of meaning and the execution of a goal are becoming part of the engineering problem. And so there's a new area of research on semantic communication and effective communication that starts becoming important. And here's just one example to explain that concept. So the goal here is to identify people in the camera view. And how this is done today is you have, on one end, feature extraction that is then transferred over a wireless link to the other side, where you have then coding that compares that with a database to give you the identity of people. Now, today, these problems, the identification of people and the transmission over the link, are treated as separate problems, and you likely end up with a suboptimal solution in the combination of the two. And you see where this is going. If I combine the two problems, and especially in a lossy channel or a low energy constraint channel, you can get to more optimal solutions if you think of this as an effective communication problem and really thinking of the goal that you're trying to achieve. So, but then it's not only about the radio interface and AI at the radio interface. AI can also help us to create a unifying network experience. We call that UNext, with a nod to Unix, the operating system invented at Bell Labs. Our vision for that network is really that you will have an infrastructure of a multi-cloud, a continuum of cloud compute capability integrated with multiple networks, really networks of networks. On that infrastructure, you then create the different network functions that you need for your 6G service. And it's important to realize that there's multiple actors there. There are the data centers, the different cloud providers, enterprise, CSP, and hyperscalers. Then also different networks. There can be satellite networks, there can be enterprise networks, there can be different access networks and the data center interconnect networks. So there's multiple actors that we need to take there in that network of networks. And then the creation of the applications need to happen also in symbiosis with the applications. So the composition of these services. And therefore, it is a very complex problem where the availability of network data and application data, the knowledge that is embedded in the AI models, really allows for an effective orchestration across these different resources, across the different actors in a unified way. So we talked about the 3 pillars, but there's more to 6G. There is also sustainable 6G, there is secure 6G, and responsible 6G. Let's start with sustainable 6G, has been a theme at this conference very much. There's more than 70% of the power consumption in a network is in the radio access network. So that's an important area of attention for research. And what you ideally want is that the energy follows the traffic load. And you can do that already with microslots, but you can do better. Actually, Shannon has shown that you need to spend the high energy only if you really want a high spectral efficiency. So you can optimize your power even better than linear, the transmit power. You can also, in massive antenna arrays, you can start think of muting segments of your antenna array, and with that, the digital front end. And if you have a scalable baseband processing, also the baseband processing. Then there's further research on the front end itself, on power amplifiers that are integrated with approaches for DAC and ADC that give you further energy efficiencies. So as an example of the importance of research in sustainable 6G. The other one is secure 6G. And here is, I take another part of our new Nokia logo, and what our external design company probably didn't realize, that there's also a quantum bracket symbol in there, by which I remember from college, we notate the quantum states. And you see here a picture of our own quantum research, where we do research on topological qubits. Why do I use that to start talking about 6G security? Well, on one hand, I'm very proud of this type of research that we do. But on the other hand, there was a guy at Bell Labs, Peter Shor. He figured out that actually encrypted code that is deemed safe today can be hacked with quantum computers. So we need quantum safe encryption. But there's more. Also, AI can actually hack encrypted code. So we also need AI-safe systems. AI also that a malicious person can try to behave using AI as a benign user, but hack the system. On the other hand, AI is also a good tool. It can help us detect anomalous behavior and malicious behavior. So there's a new cat and mouse game that is starting to happen. There's also the element of trust. We're using AI models for making critical decisions in our infrastructure. Can we trust the models? And larger, it's basically going to be a zero-trust infrastructure where you have billions of devices, various software components coming from different sources, some maybe even open source, different components, so more interfaces. So there's a huge threat surface. How do you create a trusted service in a zero-trust infrastructures with such concepts as anchors of trust and distributed ledgers, for instance? And then last but not least, also privacy. If you have this multi-actor, multi-stakeholder collaboration, how do you preserve privacy with such concepts as homomorphic computing or differential privacy?
Okay, so AI. The AI is now used so much, so many business, so many applications already. But in the future, we will use it more. And AI is now improving so fast. And we will use AI even in the 6G era, of course. And in the 6G, maybe 6G network will be AI native. If so, we need to rely on the AI more and more. If so, responsible or ethical AI is one of the important challenges to be considered for the 6G. The 6G, our 6G need to be supported. The AI need to be fair to avoid any discrimination or bias. And also AI has to be accountable and transparent for everybody to know the AI behavior anytime. And AI has to preserve the privacy or security, of course. And also has to be reliable, safe. And also AI should minimize the power consumption for the sustainable society. And this is a time schedule of the 6G development. And as you know, the variety of the 6G activities has already started all over the world. In the ITU, they approved the time schedule for the IMT30 our project. And by 2030, they will complete the specification work in ITU. And also, variety of the 6G research project has already started, including the HEXA-X12, SNS, and the ION, proposed by our parents' company, now global project. And also, we have many regional activities on the 6G. In Japan, the Beyond 5G Promotion Consortium started, and we are aggressively discussing on the 6G topics. And now, it is very important to collaborate between the 6G organizations to take a global unified approach. so that we can develop the single global standard. That is a very important point. And also, regarding 3GPP, they did not have any formal activities for the 6G, but many of the stakeholders has already discussed on the time schedule of the 6G in 3GPP. We think that maybe a requirement discussion need to be started from the release 19 timeframe and the release 20 timeframe, feasibility study on the 6G, and the specification work should be release 21 so that we can develop the first 6G specifications by around 2028 so that we can launch our 6G commercial services in around 2030. And also one more thing, and in 2025, there is a very, very important milestone. We will have the World Expo in Osaka, Japan. And in this event, we intend to exhibit the pre-6G systems so that we can show the future sustainable society in that event. So please come to Japan, Osaka, in 2025.
Okay, we're coming to the end of this keynote, and I hope you start appreciating that a large body of research work has happened. Another case in point is the progress that the Hexa-X project has made, and you've seen this slide before. So if you haven't done so, please visit the booth of Hexa-X. There's 6 tangible demos there on the progress of 6G. So to summarize, what you really should take away is that 6G is coming out of the exploration phase, and we really need to get our act together and get into the systematization phase. Thank you for your attention.
Thank you very much. Thank you. Excellent view on the challenges for research and what comes next research, right, for 6G. Thank you very much. So again, lights in the room, please. And we have time again for a couple of questions. So,
Front.
Anyone?
Oh, all day.
Sorry. Sorry. Please go to the microphone and identify yourself.
Professor Muhammad Rashid from SAB. I'm working as consultant in SAB, also in Ericsson. I have 2 questions. But first of all, thank you for impressive presentation. First question about the electromagnetic waves. I asked this question many times in this conference, but nobody answered me. Electromagnetic waves have duality nature, waves and particle. Beamforming depends on the constructive interference in the waves. But nobody studied the particle property for the electromagnetic waves. For example, now we are using the terahertz frequency. In the future, maybe we will near from gamma ray frequency. We have radiation pressure. Nobody add this factor in the equations for radiation pressure. The second question, all the antennas now using the copper, gold maybe as a material. But I think if we are using the carbon nanotube for a higher electron, we can generate it by the oscillation of the electron. If we are using the carbon nanotube instead of copper, we have higher speed frequency. Thank you so much.
Thank you. These are interesting questions, really touching on the foundations of the physics, and we should, as a community, look at this. I think the frequency domains that we are envisaging here, I think the particle properties are not yet at play. I think they, as you in your question already hinted, start playing as you get to the higher frequencies. So indeed, terahertz and photonic, that starts making sense, and there's impulse and things that you can leverage. So I think for the problem space that we look, upper midband and sub-terahertz, it's maybe an interesting direction that we need to think further. But the particle properties don't really affect that much our way of thinking. I think it's more the wave property. On the carbon nanotubes and so, interesting material science, I think. I think it is not at the maturity level that we should already take it into system designs, but it is an interesting material science that we should watch for sure. Thanks for the question.
Thank you. We have a second question here and the last one because we're already out of time. Thank you.
I'll make it short. Yeah. My name is Fred Bouting. I'm from Hyro Micro Data Centers. So we develop intelligent edge data centers that look at edge services with AI and the applications on top and try to align that AI. And we are convinced that we need to align it with the network AI as well. And so we look for collaborative opportunities, but it's quite difficult to work with, well, I'm not saying it's quite difficult to work with the large operators, but to be involved with them, because we look from the data center side and not from, I mean, we need the network, but it's not part of our core, let's say, knowledge base. So we need to have that close alignment. It's very difficult to find the right entry point with the large operators. I don't know. Yeah.
Well, you're talking operators, Nakamura-san, you want to take a stab at this?
Yeah, okay. So, of course, with Docomo is already collaborating with a variety of the partners. Yeah, but yeah, maybe some kind of the difficulty to collaborate and communicate with global partners, foreign partners. But yeah, we have already collaborating with many of the global partners to develop the applications, AI solutions to be implemented in our operators MEC, so-called Docomo MEC. So, of course, yeah, you can contact me or my colleagues, but of course, we need to develop the win-win relationship. What kind of the monetized win-win relationship can be developed? That's the point, yes.
The monetization, so the monetization is the aspect, of course, because we are not a large data center operator, we have small ones.
Yeah.
So
yeah. That should be
so that's, so I understand that you look at the big investments, but you know, we're the small ones. So that's an ecosystem that still needs to grow, I think.
Yeah, and I think in 6G it's important to enable that ecosystem. And we do consider enterprise data centers and CSP far edge also a part of that cloud continuum. And so enabling business models with the players like you are part of the architectural discussion. So let's have a further discussion offline.
Yeah, one point, maybe for the future we will deploy the more local edge. Local MEC, yes, not public server MEC. So maybe, yeah, as you said, a small size of the MEC or edge computing will be used for the such kind of the new opportunity of the business. Yes, that's a trend.
Okay, thank you very much. Then thank you once again. So, Nakamura-san.
Yeah, thank you very much.
Thank you very much. Thank you, Peter. Thank you for being again in UCNC.
Thank you.
Thank you very much. Just two housekeeping things. Don't forget to answer the survey and to vote for the best booth. Enjoy the coffee break. Thank you very much for coming.
You would dance across the floor, beyond infatuation, how I obsessively adore. That's what I do. I believe I could die in your kiss. No, it doesn't get better than this. God only knows where this could go. And even if our love starts to grow out of control, and you and me go up in flames, heaven won't be the same. Where this could go, and even if our love starts to grow out of control, then you and me go up in flames, heaven won't be the same. I believe I could die in your kiss. No, it doesn't get better than this. God only knows where this could go, and even if our love starts to grow out of control, and you and me go up in flames, heaven won't be the same. God only knows where this could go, and even if our love starts to grow out of control, and you and me go up in flames, heaven won't be the same. When you feel it, just admit it, and before it is gone. When you have it, embrace and bask it, 'cause life is yours. Ba-da-bum, ba-da-bum, ba-da-bum-dum-dum-dum. When your spirit fights and resists it, oh, don't let go. 'Cause life is too short for when we get old. It would end in remorse. 'Cause life is too short for when we get old. It would end in remorse. This is what you need. You need to know for now.
Well, should I start? Okay, welcome, welcome, welcome. Please come in, make yourself comfortable. I know it's after lunch, so it's going to be a little harder session for some of you if you are trying to get to go to sleep a little bit. But welcome, and hopefully we'll have a great discussion with more people to join, because this is a very important topic of sustainability and what 6G can do for sustainability. And, you know, I've missed my flight yesterday, so I got here late last night. But since this morning, I've heard sustainability over and over again, which I think it's a great sign that we are all committed for our journey towards a sustainable future. My name is Michaela Juhat. I'm with Microsoft. I'm also with the NextG Alliance, which is a organization similar to HexaX, if you wish, in terms of looking for 6G and the different working subgroups that deal with things like spectrum, socioeconomical needs, sustainability as well. So very good to be here. I'm honored to have such distinguished panelists here. And I would like to start by giving you a little bit of an idea of what Microsoft is doing, because Microsoft, like all cloud providers, it's a very important piece of what the next generation telecommunications networks are looking already like and will look like. And we heard this morning from Peter that cloud was the decade factor. I love that, for 5G, and AI will be the decade factor for 6G, which is extremely interesting, and also perhaps a discussion on our sustainability journey. But let's start with the Microsoft slides, and I'll let each of the panelists introduce themselves. Hopefully they'll take a few minutes to talk about the work they're doing. Myself, I joined Microsoft about 3 years ago through an acquisition of a company called Metaswitch. We used to do and still do cloud functions, network functions. And while my background is technical, I joined the government affairs team, which is a very interesting group that does extremely interesting and challenging as well as rewarding work in terms of looking at policy and regulation for different aspects of the ICT industry. Now, since I joined Microsoft, I realized that I knew nothing about sustainability. And to be honest, I'm still learning after 3 years. And we all know that this is not really something that we have to recognize as a challenge and solve it tomorrow. It's going to be a long-term challenge, but there are things that we need to do today to make sure it's not irreversible. And while you can read this, it's a planet-sized challenge, and we all need to get our forces together to solve this. In our history, and again, I've heard this right now, a question, and why haven't we done something before? And I have to say again, learning that Microsoft has started this many, many years ago. This is the path that we have taken. And Microsoft has been carbon neutral, for instance, since 2012. And as you can see, in terms of our goals, are quite strong goals, and hopefully we will meet them, although we do have some challenges. And I'll go pretty fast through the presentation. Very happy to provide any other details after that and during the conversation. But what we figured is that there's 3+1, if you wish, things that we have to look at in the context of sustainability. And it's not only energy or carbon emission, but it's water, waste, as well as what we call build a planetary computer. Maybe it's a little bit big, but it's really about the ecosystem and the environment and how to use the data that we collect to create better ways of doing things and therefore answering the challenges that we have. For each of these things, we have measures and we have goals. And this is something that I want to address because part of the NextG Alliance work that we have done in the Green G group is to figure out what are the KPIs that we need to measure. And we've heard this morning about KPIs. Very important because each company today has different KPIs. So if I talk to Orange, or I talk to AT&T, or I talk to T-Mobile, they will all come with different sustainability measures, which basically won't prove anything because we don't have a baseline and we don't have a common understanding, or we don't want to do that yet. So we have done this in Microsoft for many years. Actually, this year we have just published the sustainability report for last year. For instance, the Scope 1 emissions and Scope 2 emissions are going down. Scope 3 emissions are going up. Waste is going up. So there are things that we have to constantly manage, measure, and report. Water positive, extremely important to understand what we are doing with water, how much we are consuming. Water waste, for instance, in data centers have been reduced by 94%. Will be reduced by 94% by 2025. And clearly, the last thing is to digitize data to make sure that we have always information and ability to detect and react in terms of needs around the world. Same thing with waste. Waste is a big deal. And I have to tell you, it's very interesting reading a lot of about sustainability, obviously. There are 20 companies in the world that produce most plastic waste. You can look it up. They are probably the worst in terms of carbon footprint. They are probably some of the worst in terms of water usage. So it's very interesting to actually look at who's doing what and figuring out what can we do from a network perspective to enable these industries who are the biggest challengers, if you wish, for us to actually solve the issue and help them in their transformation. And with that, I would like to pass it on to my next panelist, Pernilla. It's a pleasure. And
thank you.
It's yours.
Okay. Thank you. Hi, everyone. I'm Pernilla Bergmark. I work as a principal researcher for ICT sustainability impacts at Ericsson, and I'm also a co-rapporteur of Question 9 in ITU SD5, which means the standardization body which is developing the assessment standards. I think that is sufficient as an introduction of me. And I will not talk too much about Ericsson here, although we have our net zero targets in place. We have done a first halving of a mission and more than that in relation to the science-based targets and so on. But I will focus this pretty much on 6G. So my first message here today is that sustainability is not a good to have, but we, humanity, we must get our act together. And a very famous quote from the latest climate negotiation meeting is the one you see in front of you. Greenhouse gas emissions keep growing, also in our sector, actually. Global temperatures keep rising, and our planet is fast approaching tipping points that will make climate chaos irreversible. We are on a highway to climate hell with one foot on the accelerator. You may think that this was said by Greta Thunberg or some activist, but actually these were the words of the Secretary General of the United Nations. So we are in a dire situation. We already know that, but it's very clear. So before continuing, I would like each of you to take a few seconds and think about a child that means a lot to you. It may be your own child, your grandchild, a niece, nephew, or just maybe even yourself as a kid. Keep that image. So here is one of mine with a friend a few years ago in a lovely summer stay in the north of Sweden. And I think This is something that we need to carry with us, that the new moonshot target that we need to have as a sector, as a North Star for 6G development, is that we need to give our children a safe livelihood on Earth. So sustainability is not just another set of requirements. This is something that we need to frame 6G. So setting the scene a bit, our industry has already developed the trajectories that we need to follow to decarbonize. And we need to roughly halve our emissions by 2030 compared to a 2015 baseline. And our recent research, as Ericsson research, shows that we have increased 5% since 2020, so between 2015 and 2020. So we are not yet on track. And then, of course, 6G will come after 2030, and then we need to halve our emissions again. So we have a quite challenging landscape. Net zero is also a concept that is gaining traction from policymakers from all over, and expectations on the industries are raising. That goes, with example, we can see the ISO net zero guidelines that were developed and published in the end of 2022 during COP. There is also this work of the high-level expert group that was commissioned directly by the Secretary General. And they are putting quite strict requirements on companies how to decarbonize. But then, of course, sustainability is much broader than carbon only. And starting on the environmental side, we have a set of planetary boundaries. These boundaries are measuring the Earth system processes, those processes that are necessary to keep our planet stable. There are 9 of them, and we are breaching several. New work published last week in Nature shows that when these boundaries that has been known for some time are combined with criteria on both safety for humanity and justness, we are breaching 7 of them. So the challenges are immense from that perspective, but also opportunities. As a sector, if we really put our efforts to it, we should really try to make a difference. And the 6G landscape that creates new innovation platforms should really have that in mind. So with that as a backdrop, switching to the 6G more closely, we have talked about the sustainability as a triple bottom line. That means that we have the environmental perspective, which is what I focus on here, but we also have the social impacts and the economic impacts, and they will be also very important, obviously. We also look at this from the perspective of the sustainable 6G and the 6G for sustainability, so our own impact and how we impact other sectors. One way to look at that, which is commonly applied, is through the 3 orders of effects. So the first order effect, that's our life cycle impact, from the mine to the final disposal, hopefully with some recycling and reuse before that happens, and all the different activities that our products and networks and systems undergo during this period. Then we have the second order effect. That is when we use our systems in other sectors, which could bring positive effects, emission reductions, less resource use, and so on. But it could also be used in other ways that have the opposite effect, because we are delivering a general purpose technology. So what we need to do is to find ways to boost what is positive outcomes and suppress what is negative outcomes. So the first order effects, that's what we call sustainable 6G, and the combination of the second order effect and the higher order effects, which is how we foster transitional changes in society and behavioral changes. That together are the 6G for sustainability area. So taking a bit of an outlook here to see what we are doing to prepare, what we need to do to prepare 6G for a 2030s world, because we are not at this point, we could know one thing for sure, and that is, of course, that 6G will not happen in the world as we know it now, because a lot of things will change. But we cannot know, but we can know some things, or we can, with high likelihood, say some things. So one thing that we can be very certain of is that the consequences of climate change, they will be worse in a 2030s world, unfortunately. And that means that we need more climate adaptation. There will also be, most likely, increasing sustainability requirements from regulators. That's what we see now. We see also that the concept of science-based targets that has really been driving the business sector when it comes to climate will drive us also when it comes to other parameters. So that starts to happen already with science-based targets for nature taking off, and we could expect probably a range of them. What we also see happening, especially on the EU side, is stricter sustainability communications frameworks. Then, of course, in other sectors are also changing, and we could help them, and we could benefit from that. But we could expect a more decentralized and load-adaptive electricity grid. We could also expect that there will be more focus on the impacts of materials, and the competition for scarce materials will grow. So that's one reason why we need to keep track of materials as 6G. And then we can see the social impacts gaining traction. They are a bit behind the environmental ones, but I think they will catch up. We know that the SDGs, as we know them, are bound for 2030, but we can be pretty sure there will be some sort of continuation or successor, but we don't know exactly what they will be. Yeah. That is a list, we can continue on it, but we shouldn't now. But it's an increasing importance of access to truly sustainable digital infrastructure everywhere. That is something that we need to take into account. And that will go for people, energy systems, the green industries, and even SMEs. And that also, we would also need to keep in mind that we need to consider this from the perspective of inclusion. It's not only in some parts of the world that we will need access to this. So I'm approaching the end of this intro remark. So I think I just wanted to comment on how I think that technology development of the different systems, access systems and telecom systems on the mobile side has evolved. So I think the traditional way have been that we have had technology challenges and even smarter systems, KPIs like latency and so on at the center. And I think we have had maybe some sustainability work historically, but it has been a bit on the side if you look at it from the technology development perspective. Then, of course, companies have worked on it and so on. But from the perspective of technology development projects, not so much. I think that we are here in the current 6G. We have improved. I think the sustainability has more attention. It's a bigger one. It has moved closer to the mainstream, and it has also been connected to it. That's what we see in Hexa-X and Hexa-X2. But I think there is still a challenge. So I think we need to move sustainability into the center, and we need to expand further. I think it's super important that sustainability is not only for some specialists on sustainability, but it's a perspective that we have in our daily work on different technology development. When we take our architecture decisions, when we think through how to signal, what kind of signals do we need, when we think through what use cases we need. We would need to put this at the center if we should really develop a truly sustainable system. So that's, in my view, how we would put the kids at the center. So I finish off where I started. The new moonshot target for the emerging 6G ecosystem is really that we should keep at the back of our mind that we need to give our children a safe livelihood on Earth, and that means that every sector needs to do its part. So it's not just another set of requirements. Thank you.
Ali?
Thank you very much. Good afternoon. My name is Ali Rezaki. I am Head of System Sustainability at Nokia Standards, based in Munich. We are developing and advancing our sustainability research from a systems perspective. Thanks very much for setting the scene and for the great presentation from Pernilla, warning us of the challenges lying ahead. I also want to stop for a few minutes and take stock of where we are today. So we are experiencing an environmental emergency today. That's clear. That's now communicated from the UN, from national governments, and from our everyday lives living through this climate emergency, and more generally, an environmental emergency. On top of that, there are disadvantaged and excluded populations worldwide. We have been hearing this in the past 2 days as well, that our technology is not, let's say, or has not been able to bridge the digital divide as it has been promised, but of course the challenge is huge. Now, against this backdrop, we are working on and researching the next generation of mobile communications. I would like to have a, let's say, I would like to step back and have a different perspective on how we can approach this challenge. By many accounts, it's been said that human nature and human disconnect has a bearing on what we are experiencing today as the climate emergency and the social injustice that exists in the world today. What does it mean? Basically, it means that we have an inability to link actions with their impact to others. That's, in more engineering terms, broken feedback loops that we have created, perhaps, or that have existed and were exacerbated with different technologies, but also, of course, social mechanisms. So, just to give an example from our engineering experience, in many projects I have worked, and let's say many of us work, I suspect, we are given certain requirements, we are given certain targets, and we do our optimizations and implementations to reach those targets. We define our boundaries, and we are concerned with what's in the boundary. But very often, some things are externalized. We are not aware fully of the implications of what we are building to what exists outside those boundaries. Now, we are, let's say, luckily being asked to optimize additional parameters. Many of us are now challenged by reducing our energy consumption in our designs and increasing energy efficiency. That's a start. And now we are asking how can ICTs in general and 6G in particular can help rebuild that feedback loop from, let's say, what we are seeing as advancement and what we are seeing as degradation elsewhere. Now, I guess, as I said, I want to take a step back and look at it from a side view and try to understand, or let's say start investigating our impact on Earth as a whole. And what I would like to talk to you today about is a branch of science called Earth System Science. It's a holistic and interdisciplinary branch of science that involves many disciplines, from geography, from environmental engineering, meteorology, and social sciences, and it's a very interdisciplinary endeavor. And what does it try to do? Basically, it's an observation, starting with an observation, that Earth is a complex system of systems. What are those systems? We are familiar with the atmosphere, of course, where our climate emergency is taking place today. Then there is the biosphere, geosphere, hydrosphere, which we have been familiar with. And on top of that, a new sphere has been added, the anthroposphere, where all human activity is taking place. Earth system science basically explores how feedback loops within these spheres and among these spheres create stable conditions, or have created stable conditions for life to be sustained on the planet. And these stable conditions are, as we well know from the atmosphere today, are being challenged by human activity. Earth system science also has methodology to analyze and diagnose, let's say, the impact of human activity on the rest of the Earth systems. And it is basically trying to show how human activity is pushing these stable systems to their tipping points, as Pernilla also mentioned. And once those tipping points are reached, with cascade effects, there will be other stable conditions established, which are predicted not to be very accommodating to life on Earth, perhaps. Now, why am I saying all of this? Like, as engineers, we like methodology, we like analytics, and we like, let's say, data-driven approaches. And I want to, let's say, frame this as a future research stream for us. We need to understand how Earth system science can affect our research and how we can contribute to it, and basically also understand our impact not only in the atmosphere as climate change, energy efficiency, energy savings is focusing on, but as a whole to the Earth system. And why is that important? We have heard several times in the past 2 days. We have our footprint, we have our handprint, and then there is the rebound effect. We are doing a lot of innovative things to reduce our energy, to increase our energy efficiency, reduce our energy consumption. But then there is this thing called rebound effect, and then if for other reasons than our own design, consumption increases of our products and the overall energy consumption of what we are delivering increases, then everything we have accomplished in terms of energy efficiency and savings do not produce the targeted effects. We don't have to be too dramatic, but at the end, our targets may not be reached. So, the Earth system science, can it help us to manage this complexity? Basically, if we look at this, we are operating in the anthroposphere with all human activity. And we know well our interaction between anthroposphere and atmosphere. That's what is being proven many times from the UN, from the IPCC Commission, and that link is very well established today. What about the others? Our impact to geosphere. Let's say we are happy with the electric cars, or at the beginning we were happy with the electric cars because they were zero emissions in their use phase, and we were driving them happily. Then reports started coming out about their batteries, how their primary materials are sourced. And we come to realize there is a huge impact to nature, to the land that holds those mines for the primary materials, and the forests that are being felled to open those mines. So there is a direct link now with that to geosphere and the biosphere, which includes the forests. And there is a link, a cascading effect as well, from mine opening and the forests being cut down. And then, of course, from there is a link to the atmosphere, which is basically the capacity of those forests to absorb carbon dioxide reducing. It's a connected world, and we have to somehow find our place in this connected world as researchers, and then we have to optimize, or let's say manage our impact to this system. And I just wanted to make analogies, as we are communications engineers mostly. We are, let's say, if we take this as a network with 5 nodes and a fully meshed network, then we can say that we exist as a slice in that network. Or we can say we exist in the data flows, in the pipes between those nodes. And our actions have direct implications. But it's a complex system. That's for sure. And ESS, of course, independent from us, have developed many methodologies to manage this complexity. They use observations, measurements, and assessments. These are very close to our hearts as well. Like what Pernilla showed a moment ago, many of the standards having been developed in ITU-T on environmental assessment, impact assessment, have these items. We have measurements, we have assessments. What we can measure, we measure as primary data. What we cannot measure, we assess from secondary data. So we are already approaching certain aspects of this methodology. Then ESS also uses modeling and simulations to tackle the complexity, which is another method we deploy in our work as well. So, just not to linger on, basically, if we follow such a holistic approach, we will have an inclusive perspective on not only our footprint, but also our handprint and the rebound effect, because we will not have only considered our direct boundary, but the other side as well. Sometimes I feel that sustainability is about our impact to the others. If we think of our impact to the others, not what we are responsible for inside the boundary, then I think we have a good chance of tackling the sustainability challenge. Then, how do we address social impact? It's a very tough question. Like in the last 2 days, we have heard some UN representatives saying that internet has failed in its promise to bridge the digital divide. Or with every next generation of mobile communications, the digital divide has been growing. We don't know if there is a causal link between that or it's just a timeline effect, that as we move in time, there are other factors affecting the digital divide that resulted in that growth. But we have to have an answer, and for that, we need to have a holistic approach as well. And I think the ESS approach could be a start. Now, with 6G, how do we connect our technology to this? We create a good toolbox with what we are researching for 6G. We have heard how sensing, how non-terrestrial networks can help observe and generate time-based, let's say, data that can be interpreted, and then a corrective action or any action can be based upon that. We have digital twins for simulation. We have already seen in some demos how this can be implemented for 6G. But in the report that I have referenced from the German Academy of Sciences, they emphasize the digital twin for the Earth, for nature. And then if we, for example, connect those digital twins together, then maybe our simulations can show us the way before, as many of us have rightly said, it's too late when 6G becomes reality in 2030. And AI/ML has been mentioned several times. Of course, there are the upsides and downsides in terms of sustainability for when it comes to AI/ML. We have to use it with the right mindset and safeguards, obviously. Security and privacy, sensing and observations, measurements, these all involve critical data. So that's also there in 6G. I guess what we can do also is to affect Earth system science from our perspective, helping it in its methodologies. It could be a two-way collaboration. I want to conclude with this. All of what I said is highly complex, and currently it might sound a lot abstract, but as a community of researchers, not only technology researchers, but social sciences and economics included, in a truly interdisciplinary way and truly collaborative way, we can hope to start this as a community. Thank you very much.
Thank you, Ali. For Lisbeth, please.
Those are panel questions. I don't think that's up to
me.
No. Yes.
Yes, here you are.
Okay, good afternoon. So my name is Lisbeth van der Perre. I work for KU Leuven in Belgium. I'm currently on a sabbatical in Sweden, and I must say it's probably the best country in the world to be on a sabbatical on if you want to think about 6G and sustainability. I have the honor to be the scientific lead for 2 of these European projects. One is Reindeer, the other one X6G Tandem. It is also a challenge, but I think it's equally challenging for the people working in those projects to have me as a scientific lead. Because I was invited to say a few words about what I'm doing or who I am. Well, maybe I can say that I'm a fan of Ada Lovelace. And Ada Lovelace, as you may know, was the first computer programmer, even without a computer being there. And Ada Lovelace, she believed that intuition and imagination were critical to effectively applying mathematical and scientific concepts. I would say that is also what we call engineering today, or we should call engineering. It's being creative and imaginative to effectively apply science and mathematics and physics. And she always also valued metaphysics as much as mathematics, viewing both as tools for exploring the unseen world around us. So I think she already talked about KVIs when she was working many, many decades ago, years ago, centuries ago. And I think that's a good thing that we also say, well, let's go back to that. But let's also be a bit maybe more creative when we talk about 6G. Now, going from 5G to 6G, what may be the difference? I know most of you, but I don't have a good view of the public. I think most of you are working somehow related to 5G, beyond 5G, 6G. So maybe who is working on 5G, beyond 5G, 6G? Raise hands. I think most of you, not everyone. And then the next question is, I won't ask you the question, but who has received this question? I have received this question quite often. Who has received the question, what will be the difference between 5G and 6G? Lots of you. And then you come up with an answer which is something you have readily available, or you try to say something you have heard from others, or you try to make up something. Well, I think what most of the answers say going from 5G to 6G, probably this is it. We will go to something which is going to offer new services, and we think about these metaverse things, and we think about drones and whatever, and we go something which will be more sustainable, which will be more green. So I think that's a positive news that very often you hear both of them together when we talk about 6G. It's not only going to be about other new services and fantastic scientific things, but maybe it's also going to be something which is more sustainable. Now you might criticize me and say, Lisbeth, you have been very lazy because you just used the same base station and you gave it a green color. Maybe it's just been greenwashing or giving it a green color, but for the rest not doing anything. Well, it's a bit lazy, which I don't think is bad. Being here in Sweden, lagom is say you don't need to overdo things, just good enough, and maybe we should think about that. Don't overdo things, don't use more energy than is needed, don't use more materials than is needed. Maybe we should think about refurbishing as long as possible 5G from an energy perspective, from a carbon footprint perspective, from a lot of the ecological impact. Maybe we should try to refurbish 5G infrastructure at least and see how long we can keep it alive. Because this is part of a course I'm giving. It's French, but anyway, I think you can understand. And every day is a school day. If we build a computer of 2 kilograms, this is what is underneath. In resources, in materials, in energy, in water, I think it's quite impressive. So we should be aware, I think, I have a colleague at University of Lund, he put on his door, here capacity is lower than infinity. For capacity equal to infinity, contact the theological department. I would say, here, zero carbon doesn't exist. For people who want to get something, 6G that will be zero carbon, please contact the theological department. Because we know Shannon's law, and we'll say we know that capacity cannot be infinite. But let's be honest, if we know the laws of thermodynamics, and I think many of you have sometime have to learn something on thermodynamics, you will say the same thing. Zero carbon doesn't exist. I have a colleague working in the energy department. Anytime I come with, we'll go for zero energy devices, we build zero energy IoT, he says, that doesn't exist. So I think we should be careful if we are engineering. We are not in the theological department. If we start building new hardware, we will have an impact. And just to give you an idea, if we would extend the lifetime of our appliances, like, for example, your smartphone, I'm a fan of the Fairphone, by the way, but also your washing machine, other things, or your vacuum cleaner. I don't know whether you're aware of it, but in Belgium, if you go to repair cafes, the first thing, the most things that are the most repaired thing is the vacuum cleaner. And I think even as an engineer, we are electrical engineers, suppose it's broken, and I had a problem a few months ago, and you can fix it for yourself. As an engineer, it's an existential pleasure to say, wow, I have it working again. As long as, of course, if you don't spend the money for something else. But to avoid saying, it's my excuse to buy the robot, which could work on 6G, it doesn't even need 6G. It's also an interesting idea. Maybe I can keep it alive for some longer time. So one of the things I would say, what if for sustainable 6G, instead of saying we will start deploying it in 2030, what about targeting 2033? Maybe that would be a sustainable impact. So I know that I'm not going to be, the Nokia guy is looking angry at me already. I know there is this call for sustainability projects next year of SNS. I think I just talked myself out of any project proposals by saying this. But I think we should consider it. And if we say we should start deploying it, maybe then we should do something else. Maybe we should think about what Ada Lovelace said, and she said, what are her tools and what are her values? And being more creative, being more imaginative, and what would she do? We don't know, but what if we consider the way she looked at things and maybe look a bit further than the internal things? Well, we talked about what could be the difference between 5G and 6G. Now I want to ask you, what could make all the difference if we go from 5G to 6G? Could we make all the difference? And if people ask me, what would be for you, what do you think is 6G? Honestly, I'm not looking forward to AR and XR personally. I'm not a gaming person. I get a bit sick from using some of these devices. I prefer personal contacts and holographic images. So I'm not so fond of some of the very high data rate things that are being proposed. I'm a little bit afraid of AI also. So what I typically answer is, well, I hope 6G will be what the LED lamps have been with respect to the old lighting bulbs. I hope that if 5G is still like this, we get a very good coverage, we have very good lighting, we can do fantastic things. But what we really use as an energy consumption compared to what we put in, and not only energy, but also carbon footprint in general, is extreme. So if we mind the losses of such a light bulb, what really is useful, and then, for example, of course, we can use terahertz systems and get something over the air with narrow beams, etc. But if you consider the total energy consumption of bringing things to terahertz, and the PAs that we cannot make more efficient than what they are today, I don't think physically we can go much further. The digital processing, we will be able to digital processing at fantastic speed, and we can parallelize and whatever. I agree, but think about the footprint of those things is extreme. So for me, I hope we could think in a different way. And we say, maybe we should see how we could make the LED version of lighting. Maybe it should become a big disruption. And how could we do this big disruption? Well, first of all, mind the losses. Don't only talk about energy on the air and transmit power. Think about everything before you have any energy on the air. And maybe try to build something which is much more gradual, which is built out of a lot of small things that together consume much less, and where we don't only put things there in a lagom way when we need them and only switch them on when they are needed, like these LED things that could be much more gradually switched on and switched off. And also in deployment, we don't need to put 6G there once at all. So I think there's plenty of opportunities and challenges in R&D for that. And even then, but my last slide, I see, have disappeared, but I will say, I had another slide with a lot of nice things you can do with LED lamps. And also hearing our chair saying, maybe a lot of the footprint is not in electronics. Maybe, for example, it's in the construction. Well, we're doing a project together with people who work on circular buildings and circular houses. And if they ask for sensing, they don't ask for terahertz to monitor their buildings all the time. The buildings will remain there for a very long time, for 10, 15, maybe 20 years, 25 years. And then we would need to recycle and still know what's happening. So the kind of sensing and connected sensors application they ask for is very different from what we have been talking about. So I think we can really address very important challenges, but then we should reconsider, I think, what are the main targets for 6G. And I would say maybe it's not the application I have shown in the beginning. Maybe we should analyze what are the tiny things, the tiny connected sensors that could make a huge difference all over and address other sustainability challenges. Thank you.
Thank you. Hi. Okay. The mic is working. Hello, everyone. I want just to begin by thank you for the organizer for inviting me to speak, and thank you, Mekale, for having me in this panel. My name is Azdin Gati, and I am working within Orange since many, many years. I'm working since 10 years on carbon assessment, basically. Yeah? We are working on carbon assessment, and we hope the next decade, we spent like a decade working on how to optimize the carbon footprint. I hope the next decade will be how to, let's say, monetize the carbon. Okay. My presentation today, it is something about sustainability. So our talk today is about sustainability, the challenges and the opportunities. Huh? So the challenges, we know them more or less. And we are looking for the opportunities, as said by Elizabeth. Elizabeth, you said that we don't know what is the 6G. Nobody knows what is the 6G, but I know something. Following the discussion that we have during these 3 past years, it will be sustainable. I'm pretty sure that everybody is talking about sustainability. So it should be. It should be sustainable. So we have here the roadmap to the 6G. I have just 4 slides. Huh? My presentation will be very short. I have just a couple of messages that I wanted to share with you. The first one is this one, is to say that it's not late to make 6G sustainable. It's not late. I think it's not late because we did not start standardization, so we will not have people saying the radio interface is already designed, so we cannot do. The frequencies have already been chosen. It's not. By the end of the year, we have the WRC. We will fix the frequencies. So I hope we will do the good choice. So it's time. It's already. It's time to work on this, and we have the opportunity to influence. And now is the perfect time. Why? Because it's always this is what's happened for 2G, 3G, and 4G and 5G. In 5G, not really, but in 2G, 3G, and 4G, it was the case. We designed the network and then we optimize it, and it's really horrible to optimize something that is existing because you don't have enough margin. Okay, this is my first message. The second one is something that we are working with some of you here in the audience. Is in ExaX. ExaX is one of the projects that we are working on with many other colleagues. So this notion of KVI, I really like it. We are moving from a world of KPIs, performance, more data rates, more lower latency, densify the connections, the capacity, and so on and so on and so on. Okay. So we know that, and we will continue that, for sure. But the other thing that we are working on is the KVI, the value. What is the value? For example, let me give you a concrete example. In France, for example, we are pushing our regulator, to stop the competition between operators, measuring what is the peak data rate. It has no sense. For some heavy users, they will need the peak data rate. But for the common population, the peak data rate has no sense. So why not working on something which is the minimum? What is the minimum data rate that everybody needed? Everywhere in every place. Okay. So changing our mindset. From KPI to KVIs. It's not simple. So KVIs can include, of course, efficiency, environment, security, resilience. Resilience is something that is really it's the hype of these two last years, especially, unfortunately, because of the energy crisis and the war that we have in Europe. But yeah, the question of resilience is really, resilience is not only energy. Resilience, you can include security inside, and so there are a lot of things in security. So yeah, this notion of how to make the two working together. Sorry, I'm too late. I just wanted to share this with you. It's not published yet. This is something that we are going to publish. And this is our assessment of our carbon footprint, okay? Following the GHG protocol. So scope 1 and 2, basically electricity, the consumption of electricity, we know it. For example, in Orange, today we are spending like 500 million euro per year in electricity. So this is scope 1 and 2, only scope 1 and 2. And you see scope 3. Scope 3 is the biggest part, okay? I'm talking about carbon. I'm not talking about electricity, carbon. So if you have a look to this carbon footprint, you see that really when you assess the carbon, there are a lot of rooms of improvement. The carbon is not the problem of, this picture is only specific for me as an operator. We cannot say that it's the same picture for Pernilla in Nokia, Pernilla in Ericsson, or Inali in Nokia. OEM has, you have another picture. We have this picture, and it's continued to improve. But just to show you that, we have the carbon footprint of purchasing material, network elements, purchasing services, the use of sold equipment and the customer equipment. So you see these big, we call this the high runners, the 4 biggest parts of where we have our carbon assessment. This is to say that the carbon is not the business of just an operator with an OEM. No, it's the business of everything. For example, in Orange, our biggest part the biggest part is not the mobile. The biggest part in carbon is not the mobile, it's the fixed. Why? Because we continue to deploy the fiber. And to deploy the fiber, we have to, I don't know how to say it in English. We have to put the cables, we have to put the towers, and you spend a lot of carbon in this, okay? And also maintenance of the networks. Maintenance of the network is huge in terms of carbon footprint. We have the question of manufacturing VS usage. Of course, for an OEM, from their perspective, it's 20%, 80%, I think. 20% for manufacturing, 80% for it depends on the product, I know. Yes. For us, if we take everything, passive, active, civil works, and it's 50-50 between manufacturing and usage. But taking into account everything, okay? And I will finish just by this, but this is just an introduction to our panel. So we have to do all of this, for the 5G. Monitoring, continue the effort on monitoring, continue the effort on consuming 0 watt at 0 load. And of course, something that was mentioned, I think, by Elizabeth, refurbishing and the reuse and extending the lifetime. why not extending the lifetime? Some of the products that we have in the network, they have a duration of 10 years, something like 10 years. We want to extend it. And we want to develop, for example, marketplaces to stimulate this the marketplaces for refurbished elements. I mean, we are not obliged to buy everything at each time. We can recycle and reuse. So that was my main messages. Thank you very much.
Thank you very much. I think you have heard quite different presentations, and I'm very excited to open up this discussion because it's quite diverse, as I said. I mean, you know, from looking to the future and our kids and how to live our world to, you know, do we need 6G at all, or when do we need 6G, to looking at systems as a, you know, from an Earth perspective, to, you know, a very clear perspective from an operator on what are the needs and how their view of the world looks like from a sustainability perspective. We do have some prepared questions, but before I start, I would like to see if there are any immediate questions, burning questions from the audience. Okay, just prepare, you know, a few questions, but I'll start. Oh, there is a question, sorry. Please, go ahead. Could you please go to the, yeah, thank you.
Thank you very much, all the panelists. Very interesting discussion. My name is Konstantinos Dodini from the University of Luxembourg. I'm not sure if my question actually is directed mostly to a person coming from a vendor or a person coming from a mobile operator, maybe the latter, but anyway. Anyone can jump in. So I would like to direct it actually to Azadin from Orange. So I liked very much actually the idea that we need to focus more on the KPIs instead of the, let's say, KPIs. So instead of going to some traditional metrics like peak rate, we need to maybe mostly focus on satisfying the minimum data rate that the users actually demand. But would that mean that we need to change our mentality related to the deployment in the network, so to go to small cell densification? Because we heard in the morning from Professor Rappaport about going to higher frequencies, so that means we will need to go to a highly densified network. So, I mean, how does it play out, I mean, with respect to the energy efficiency? Because, I mean, in my view, at least correct me if I'm wrong, actually densifying the network with small cells, so nodes that have active components, power amplifier, means that we will, let's say, induce a very high energy consumption. So we need to plug this, actually. I mean, who, let's say, is going to pay the electricity bill, plus, actually, all the energy consumption, the CO2 emissions, not only about the energy consumption, but also aesthetically means, as you said, about the carbon, the CO2, actually, that may come from, let's say, that they need to dig, actually, to install cables. So we need to power those nodes. We need to create power cabinets. We need exactly cables for that. Even if we don't go underground, if we go with over-the-air cables, still aesthetically, it will create something that is not sustainable. So it's not about the, let's say, carbon footprint. It's also the aesthetic means. So sustainability is also about the aesthetics, not seeing everywhere cables and stuff. So, I mean, mainly that, actually, how this idea of small cell densification is compatible with the fact of, let's say, sustainability, energy efficiency, etc. I mean,
can I try to do the question? So I guess your main question was that cell densification actually could lead to increased energy consumption, and is that a good thing or not, and are you taking that in consideration?
Yeah, let me give you a concrete example, okay? In France last year, we were obliged by the government to extend the network by 1/3 because we want to, for inclusion, even for white spaces, what we call white spaces, I mean, spaces where there is nobody. Okay, you can increase, you can accept to increase the power consumption. You can accept, we have to accept it. I mean, it's not a problem. I mean, we are deploying networks to connect people, and we have to accept that there will be an increase in terms of power consumption. But then the question is how to manage this energy. I mean, you can, for example, generate green energy by solar panels, for example. You can activate on this by densify, I mean, you densify, but you deploy sleep modes, for example, to make it, to put it in a dormant mode when there is no traffic, and other, I mean, many other levers. So there is no opposition, I think, between densifying and increasing the power consumption. And as I said, things are not opposite. Really, you don't have to think it like this. Think it in the way that sometimes you have to accept you increase the power consumption, but sometimes it's not. I mean, it's not. For example, let me give you an example, horrible example: base stations which are installed in stadiums. Okay, why they are always on? They are always on. We have a football match 1 per 2 weeks. Okay, why they are always on? Because we don't know how to switch off a network. We don't know how to do that. We can activate some sleep modes, but we don't know how to switch it off completely.
Yes. May I jump into that? So I think on a technical basis, the good thing is if we go for cell-free networks, which is one of the technologies for 6G, and we start thinking about how we could build those, I think there's plenty of possibilities to do much more gradual sleep down and sleep up. And I think we should consider that in the system design up front, that part of the thing would be in the system to make sure that you can switch it off to a large extent in a lot of situations, in different places, at different moments. I think that is part of how 6G could do much better than 5G, is if you design upfront knowing that very often you want to switch off part of it, and the cell-free concept, I think, is very well supporting that. And then the hardware should also support that you can switch it off, that it's not like it's on or off and you have to wait 5 hours to get it on again, that you have all kind of sleep modes in the hardware that the system level can incentivize this and vice versa. I think that's one thing. Another thing I want to fight a little bit, I think it's not because it's been said this morning that we should always go to higher bandwidth and therefore to higher frequencies. That is a given thing for 6G. And I think we have also seen presentation by Nokia that the golden frequencies maybe are the ones that will be best serving like the digital inclusion and covering with the white spaces and what on. I would avoid that we say, well, let's immediately try to deploy the very high frequencies that need a very dense deployment everywhere. I think that is not a given thing. You kind of stated like this is the vision, that's what we should do. I think it's more correct probably to say let's do that on places where there is a capacity shortage where you need a very high throughput. But for the white spaces, as you've been talking, I would not go to sub-terahertz, to be honest.
Thank you very much for the question.
Thank you.
Yeah, please go ahead.
I think we are missing something here. In 5G, there was a big step toward reduce the power consumption. If you know, the Shannon law says whenever you have more bandwidth, it's linear with the capacity. Whenever you have a SNR, it's a log with the capacity. So by the regulator, which gave us more frequencies, actually, for the same capacity, if you look at that, in order to achieve capacity, a certain bandwidth today, we are doing QPSK 60, comes 64 QAM to 56 QAM. If you go for QPSK to 64 QAM, it's almost 20 dB in the power. But if you give me 4 times the bandwidth, it is just 4.
Yeah,
so
but
that
that
is like 100 to
No, but that's
10.
the metric of transmit power. But if you look at the efficiency, before you make that, I think a typical power amplifier today at very high frequencies, if you achieved 15%, that's a lot. So we should
I'm not talking yet about the high frequency. I'm talking the...
Yeah, but that's the point also with bandwidth. I think we should be careful.
I will come to that. When you go to the high frequencies, okay, still, if you do densification, then most of the time you have line of sight. Again, you transmit, instead of 12 dB per double the range, you are doing 6 dB double the range, you're getting less capacity. So as far as the technology in 5G, we did a lot of steps to move forward in this. The regulator is helping us, give us more bandwidth. So today, I can tell you for sure, we are almost for the same data rate, same throughput, we are almost 10 times more efficient than the the 4G that is only 20 megahertz relative to 100 megahertz bandwidth.
Can I be provocative?
So we are not so bad in situation. Yes, we have.
I think I will be provocative. If you go for the high speed, yes, but the 0 watts, what do you say, 0 watts,
0 watt, 0 load.
I think for 0 load, we have been getting to something which is much worse than before. For the maximum, and I'm a massive MIMO addict, I think for the high loads, I agree with you, but for the 0 loads, 5G is worse than 4G. And in a lot of situations, we are far from the maximum load. We are into not the 0 load, but closer to the 0 load. And then, unfortunately, 5G is worse than 4G.
I agree with that. If you don't have capacity, okay, you don't need to transmit, then don't transmit. It's okay. I'm not argue about that. But again, I'm talking about because when we are going to 6G, we want more capacity. It's not 0 load. So that's the situation there will be. So that's what we have to think.
Thank you very much. I think that's a very good point, though, to remember that XG actually brought a lot of efficiency gains. And it's not all very, it's not very bad from an ICT industry where we stand. So where we stand is that we are 1.5 of the total carbon emission and perhaps 3 or 4% of the energy consumption. So from an ICT perspective, I think we are pretty good in our standing. That doesn't mean that we don't have things to do. And I just want to go to perhaps the first question that we had prepared in terms of the challenge, but I want to frame it in a way that I think of a challenge. So given that I'm from Europe, but moved to the US for many years now, I realize that money, 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 it's not just a song by ABBA, but it's actually what makes the world go round. And in terms of really challenge and perhaps a response is that we need to make things affordable. We need to make 6G affordable. Not only for the consumers, but for the people that make the equipment, for the people who provide the service, for the people who don't have anything. And that's the only way, in my mind, you can do that. It's to rely on innovation. That's what we have done. All our lives, in all our history, we haven't stopped the consumption. In fact, consumption actually goes on, and that's a challenge to the Earth theory, because I don't think it's a loop issue, broken loop issue. It's more of a fact that we don't put what's the right loop, and the loop, it's, we do something for something, which is money, and then it goes back. Does it make money? We do it again. Does it not make money? We start something else, right? So from that perspective, I would like to frame the challenge and ask each of you, what do you think the challenge is for 6G? And maybe I'll start with you, Pernilla.
You mean from the monetarian perspective?
Well, I thought that's the biggest challenge.
Okay, that's the main challenge.
That's my perspective, but maybe you have a different one.
No, but I would probably say, in line with with my presentation, that it will be the integration of sustainability perspectives and the technology development, that we are not really there, and we are coming from quite different perspectives. And maybe the question we had over there, which had maybe to do a bit with things like, or thinking like sufficiency and that kind of, I don't know, concepts or that we are used to be a sector which is aiming for faster, slower, you're aiming for the extremes in performance. But in reality, in 6G, we would need, I think, from a sustainability perspective, much more of flexibility, and also to have the full life cycle perspective. And to get that, we really need to integrate the technology knowledge with the sustainability knowledge.
Okay, thank you. Ali, what do you think?
Thanks for the great question. For me, having lived through the generations of mobile technology, I think our biggest challenge is managing complexity. And complexity results in all sorts of impacts. And One of them might be cost, one of other is accessibility for industries, for individual operators, but also verticals. That is also a challenge for sustainability. And like in the engineering world, it's over-engineering complexity. And in the standards world, we have to get 6G through. It's about addressing every single option, every single, let's say, requirement, turning it into a design, and more and more of what we are building into the specifications is excluded from everyday usage. We have some statistics, but sometimes it's perhaps even 10%. So why is that complexity there? And that adds to cost, that adds to the, let's say, zero load energy consumption. We have to manage complexity, I would say.
Thank you. Very, very interesting answer.
Yeah, very quickly, two points. The first one, I said it, as an operator, we don't know how to switch off a network, and we want to switch off. We want to have the ability to switch off. I mean, it's not normal that we cannot switch off. We can have partially a switch off. We call this the deep sleep, but we cannot sleep. So I mentioned this point. I think in the next generation we need that. We need this flexibility. The second point is something that we work with Pernilla, is the LCA, life cycle assessment. We will ask. I mean, we signed with the Dutch Telecom and Orange. We will at each time we will buy something from this year. We will ask for an LCA for every single product that we buy. An LCA means an assessment of manufacturing, usage, end of life. Okay, but we need the two first because these are the biggest. We want to simplify the process for this. It's too complex, the LCA. The life cycle analysis of the product, I mean, we cannot compare it for the moment. I mean, I cannot say this one is better than this one because this carbon footprint of this one is better than this one, because the assessment still, there are still complexity. So I hope we will simplify.
Please go
May
ahead.
I comment
Yes.
on that?
You want to react? Yes.
No, yeah, I have a mic. So the life cycle assessments are complex because they are modeling something complex.
Yeah.
And the only way to make it simpler and especially to make it comparable is to develop specific scenarios. And that means that the results that you produce, if you simplify, the results will be less accurate. And if you create comparable conditions, that means that you will get the comparability, but at the same time, the results will be less specific to the conditions that they are modeling.
Yeah.
So it comes with a cost, but it's possible, and that's why we are working on it in ETSI and ITU. But we should be very aware of the limitations, and it's not LCA is like a bad methodological approach, but it's an important one. If we will understand things at depth, then we will need to do studies at depth.
Thank you.
Any comments?
Elizabeth?
Yeah, but coming back to the business model question, I think that is a huge question for IoT. For example, we could develop very novel things to have IoT supporting circular industry, which is, I think, for a lot of more ecological impacting industries a very important thing to go more circular. And we could define new IoT networks and solutions to support that. But where is the business model? Currently, people have said IoT is a 0 billion market. And I think, how could you, for example, have incentives for saying, suppose I put connected sensors and in 25 years from now, when something needs to be recycled or could be reused, I will be able to tell you what it is and where it is. Where is the business model? I think that is a huge challenge.
Thank you. I agree. And although it's all very interesting and very true problems, and going from very concrete to putting networks to sleep or thinking about the complexities. I want to turn back to you and see if there are any other questions. Please, go ahead.
Hello, thanks for organizing this very interesting panel and your talks. Talking about refurbishing, I was thinking of generations of networks like 2G, 3G, 4G, 5G. Now we talk about 6G, but 5G isn't there yet. It's not deployed fully yet. And then now, another layer of network that we talk about and deploying it. And should we think about a new, like a much more different way of deployments, like instead of this traditional way of network deployments, where you need it's a cellular-based deployment where you need to put a cell and it has to cover all around this, wide coverage, whatever, the way we calculate even coverage and the performance of a network. I mean, even the regulations pushing like operators to cover, 99% of the area versus the population and so on. I mean, with the new generation, do you really need to do that? Then what happens to the sustainability? I mean, you have to produce all this equipment, buy that, and have to cover all over the place with this new 6G. Or do you foresee like a new way of network deployments? Like, can all these networks, are we going to throw away all these? No, we never do that. They are going to stay. Of course, we always talk about backwards compatibility. They are going to be there, of course. There is a lot of redundancy here, first of all. Is it sustainable, really? It's a very basic, sustainability issue that, we are creating a lot of redundancy, first of all. I mean, we shouldn't, I think, talk about 6G as a single, alone solution. We should look at our networks. Now, we already created a lot of redundancy. What are we going to do with this existing, network, first of all? What do you think about that? And on top of it, what is going to be the 6G? How should we approach this network deployment problem now? Are we going to do the same mistake again and again in every 10 years? That's my question. Thank you.
Thank you very much. I think it's a question that I always have. So just 2 seconds. I come from a telecom background. I joined Microsoft, and I said, look, every network has to have 5 nines. And they look at me, it's like, what's that? Right, so it's all this redundancy that we build. You have to have 4x basically because you have local redundancy and then you have geo redundancy and you have all that and you build, and it's a huge cost. Now, having said that, I know that the wireline networks have consumed a lot of energy and still consuming, and operators like T-Mobile have actually gone from wireless completely to actually virtual wireline to actually virtual wireline services. So they removed all the switching gear that consumed quite a bit of power. Having said that, so we are making positive steps by going to the next generation networks, but it's a very valid point that you also brought up that, perhaps we do need to think more about refurbishing. So,
may I?
Please?
Yeah. C-check. Be careful about the false good solutions. Let me give you the example of 2G, 3G decommissioning. Okay? If you decommission a network, okay, you have to ensure that people who are only, because there's still, that are only 2G, 3G. They have mobiles which are only 2G, 3G. You have to migrate them to 4G, okay? When we do the assessment, that's why I'm saying that the carbon footprint is the essential thing, okay? We have to evaluate the end-to-end, okay? The gain that we have lowering the energy consumption by decommissioning the 2G and 3G was completely compensated by the carbon footprint of migrating the people from 2G to 3G with the handsets. Moving from because you have to fabricate, you have to manufacture new devices. So you have to, and you have to take it into account. So there is a kind of a balance between the two.
But that's exactly what she's saying. Why should we go to the next generation when we have a perfectly Or if we go to the next generation, should we think about completely new design as opposed to going through the next 10 years of 3GPP development? Please.
So I don't think I have any answer to that, but I think that is exactly the kind of conversations that we would have if we put sustainability as a center. And I think, you know, as engineers, when we are developing something, there are a lot of boundaries. We try to optimize something within a boundary. And when we add the sustainability perspective and not only the energy consumption, but the materials consumption to this equation, we get yet another boundary that we need to optimize towards. And when we start doing that, we will ask new questions, we'll probably come up with new solutions, and that will be new innovations. So I think that what you asked here, yeah, maybe we should do it in another way, or maybe we are doing it in a good way, but we need to tweak it a little. But it's exactly the kind of conversations that we need to have.
Yeah, I also indeed agree. This has to be looked at in a holistic way. You know, we are not only working on carbon emissions, but we are also working on circularity. And in standardization, but also in research, there are several steps before, let's say, equipment can be decommissioned. You can remanufacture it, refurbish it, and then at the end, if nothing can be done about that, then it is, let's say, recycled. Then, of course, we have the analogy from the light bulbs. When at home you replaced your incandescent light bulbs with LEDs, or in between you used the fluorescent bulbs, what was the motivation? And indeed, as we include new parameters into the equation, we try to optimize them. And Azettin brought a very good point. We cannot only think of the network. We are now trying to understand the network enablement effect for UEs, but also data centers. So end-to-end, this is, there are lots of things to consider. And hopefully in the 6G transformation, this will have been researched enough, and that transition will be managed in a much better way.
Thank you. That's any other great questions, please come. We still have a couple of minutes, please. Maybe this will be the last question, depending on the time, but please go ahead. Thanks.
My name is Jos Pereira, working for TNO in Netherlands. I have a question for the panel, because this was like a red thread hearing that the terahertz and the power amplifiers can do so much in terms of efficiency. I recognize that there's a limit there. And then we could hear from Orange that there are some challenges in switching off to do so, and then to go about it, to calculate or to have some measure. Then we could hear in terms of if we should build scenarios to, well, to have a better view, to be able to better compare. And now the question comes, okay, good, how to build such scenarios? Because what I've seen, let's say, with other topics in the past, if you are too early, they are all over the place. We're still in the vision phase. We don't have a clue what 6G will do. If you are too late, there are already vested interests. So some scenarios are more important, let's say, for certain parties compared to others, because they had to make themselves decisions. So then you get stuck, and there's very hard to reach consensus. How can we do that? Or how can we go about with 6G that we don't get stuck in either approach, let's say, too early or too late?
Thank you. Thank you, and please go ahead. I don't know, let's start from you.
I think many years ago, and Louis was there, we had the Earth project where a lot of it started with analyzing what is the situation. And this is an unfortunate situation that I have colleagues, for example, not from my university, analyzing carbon footprint and so on. It's very difficult to find funding for analysis work. You have to show that you're going to change the state of the art and that you bring a contribution into innovation. And so if you see evaluating project proposals, what are all the questions you get? If you say, I'm going to build a model that allows to compare and to assess, it would be very difficult to score on any of these things, even in getting papers accepted. It's very difficult to score if you say, I'm going to bring an analysis that points this out. So I think we should somehow also, as academics and scientific people, reward that just clarifying the full problem and trying to make these models and comparisons of total impact is something we should value better, I think.
Well, quick one, because we have only 6 seconds left. Each of you. Go ahead, Ali.
Yeah, thanks. I think this has come up several times during these days as well. While when 6G deployments will be only beyond 2030, how can we do assessments today? And the role of simulations, digital twins, this has been emphasized, and it is indeed the case. And for sustainability as well, we should use these opportunities and embed these into our research projects. Every technology has the life cycle as well. We start with, let's say, theoretical research. We move to an applied research phase. We use the POCs, and then we have the standardization, then implementation and deployment and decommissioning, etc. So we are in that process somewhere in the research phase, moving into, let's say, proof of concepts, as Peter was saying this morning. So indeed, we have to be mindful of where we are, but use simulation as a key opportunity.
Thank you. We are at the end of the presentation. I'm sorry not to give you a chance to respond, but I think I want to thank all of you for staying with us and listening to us. And if you have any questions for the panelists, please approach them and have a great rest of the day. Thank you so much.